Okay, going to be working on the solutions here for the section 2.5 linear equations. What we want when we're dealing with a linear differential equation is something of this format, where we have some function of x times dy dx plus some other function of x times y, and then equals g, which is some other function of x. And before we can begin this process, what we need to do first is get a leading coefficient on our dy dx term of 1. So we're going to divide through everything by that function a sub 1 of x. So you do that on all sides here, and eventually that leads you to this final format, which will look like dy dx plus some function of x, p of x, which is going to be very important to us, times y, and then equals some function of x on the right hand side. Now once we've done that, what we're going to do is find what's called the integrating factor, and to do that we will take e and raise it to the integral of that p of x function, and integrate that with respect to x. Now once we get that integrating factor, we'll multiply both sides of this equation by the integrating factor, and then amazing things are going to happen after that. So let's go ahead and just work through an example, and we'll kind of get a feel for how these things are going to work out. Alright, so our first example is dy dx equals 5y. And this is not quite in the form we need. Let me move the 5y over, and you'll see how when we move that 5y over, it will look more like what we need, which is dy dx plus some function capital P of x times y equals some function of x f of x. So now we can identify that negative 5 is actually our P of x function, and then the 0 is our f of x function here. So we are pretty much set, and now we go about trying to find the integrating factor. So to find the integrating factor, we need to figure out what e raised to the integral of p of x is. So p of x is just negative 5, and we're going to integrate that with respect to x. Now that integral is very straightforward. The antiderivative of negative 5 is just negative 5x. And we will not put plus c here because we will have a constant of integration at the very end. So we'll wait till the end to add any constants. So that is the integrating factor. It's a very important piece of this problem. Now what we'll do is we will take our equation, this line right here, and we're going to multiply both sides by the integrating factor. So e to the negative 5x times dy dx, and then minus 5y times e to the negative 5x, and then we multiply the right hand side by e to the negative 5x, and what we wind up with is a 0 on the right hand side. And then this is the key to this whole section. It's what this new thing we've created here actually becomes. And I'm going to write down first what it is. It's going to be d dx of our integrating factor e to the negative 5x times y. Alright, so this will always be p of x, sorry, I messed that up. It'll be e to the integral of p of x dx. It'll always be that integrating factor times y. And the reason why this works is because if we were to take the derivative, because that's what this means, take the derivative, right, of this product, we would just do product rule. So let me show you. If I did product rule on this, I would first take derivative of this, which would be e to negative 5x times negative 5, chain rule, times y, plus now the derivative of y, which is dy dx, times the other function e to the negative 5x. And if we look at this, this is exactly what we have up here. Okay, so if we put those together, right, we get those two up there. So the derivative of that product is equal to our left-hand side up here, right? And that's always going to be the case. All right, so let's see. Let me just come back down here and just rewrite this. We have d dx of this product is equal to 0. And now what we're going to do is just integrate both sides with respect to x. I'm going to integrate here with respect to x, And the reason, the fact that we're doing the antiderivative of the derivative, these just wipe each other out basically because they're inverse operations essentially. And all we get is just that product. And then the antiderivative of 0 on the right-hand side is a constant. And now we just solve for y. So y is equal to c over, I'm just dividing both sides by e to the negative 5x. And I'll just write that a little different. I'll bring that e up, and I'll change the exponent, to positive. Okay. Boom, there it is. So that's what y is equal to. That is our general solution here. Y equals that. Okay, so that's generally how we're going to go about these. Let's take a look at another example. So dy dx plus 2y equals 0. And this looks exactly like the form we need. So I can identify right here p of x right there. So I'll get my integrating factor right away, e to the integral of just 2 dx, and that's just e to the 2x. So now we multiply both sides. Now I'll do this one more time. I'm going to stop doing this at some point. So I multiply the left side by this, integrating factor, multiply the right side by that integrating factor. On the left-hand side, we know just by design that that is the derivative with respect to x of the product e to the 2x, which is our integrating factor, times y. We don't need to show that. We know it's true. And then the right-hand side is still 0. And now we integrate both sides with respect to x. So integrate, and we get the product here, e to the 2x times y equals some constant. And then we will divide through by e to the 2x. So this is going to become y equals c over e to the 2x. And I will bring that e up. So c times e to the negative 2x. And that is the general solution to this linear differential equation. All right, moving along. Let's look at number 3. So we have 3 dy dx. That's the first time we've had something in front of dy dx. Plus 12y equals 4. And everything else looks pretty good. So I'm going to divide through by 3 first. So everything gets divided by 3. And now I can see my p of x here. This is my f of x, which is not 0 for the first time. That's okay. I'm just going to keep working this. So I need to find the integrating factor, e to the integral of 4 dx. And that is e to the 4x. So antiderivative of 4 is 4x. So I'm going to multiply this left side by the integrating factor and multiply the right side by the integrating factor. Now, to save myself some time, I know the left-hand side, at the end of the day, is turned into the derivative of the product of the integrating factor and y. Now, the right-hand side is that 4/3 times my integrating factor. So that's a little bit different. This time it's not 0. That's okay. Now we just integrate both sides with respect to x. So integrate. The left-hand side is e to the 4x times y. The right-hand side, I'm going to pull the constant out. I'm going to integrate e to the 4x dx. Now that's a pretty straightforward antiderivative. I'll just assume you know how to do that. There's a little chain rule involved there. You're going to get a constant of 1/4 that you need when you do your antiderivative, and then plus c. And now on the left-hand side we have this still. Now we solve for y. So I'll go ahead and just divide through by e to the 4x, e to the 4x, e to the 4x. They're gone here, and then here they're gone also. So that's going to leave me with y equals, let's see, these 4's are gone. I just have a 1/3 there. 1/3 plus the constant over e to the 4x, e raised to the 4x. So I'm going to just write that as e to the negative 4x here. And this is our general solution. All right. That was number 3. Let's look at number 4 here. And before I go much further, let me make sure I'm recording. I am recording. Okay. So number 4. Okay, now we have x in front of dy dx, and then we have plus 2y equals 3. So right now I need to get rid of that x right there. Okay, so I'm going to divide everything by x. So dy dx plus, watch the way I write this, 2 over x times y. I'm keeping the y separated there. And then 3 over x. Alright, so this 2 over x is our p of x. So I need to find my integrating factor, e to the integral of 2 over x dx, which is equal to e to the, I can pull the 2 out, antiderivative 1 over x dx. And the antiderivative of 1 over x is natural log, so we get e to the 2 natural log of the absolute value of x. Now I'm going to use property of logs to push the 2 back up onto the x. So I get e to the natural log of x squared. Don't need the absolute value anymore because I'm squaring. And finally, the natural log and the e are inverse functions, so they kill each other off, and we're just left with x squared. So our integrating factor is x squared. I'm going to multiply both sides of this equation by x squared. Now again, we know the left-hand side just turns into the derivative of the integrating factor times y. We don't need to show that. But the right-hand side just turns into 3x. And now we integrate. So when we integrate, we get x squared y equals integral of 3x dx. Actually, should have just done that mentally. The antiderivative of that is just 3 halves x squared plus some constant. And now we solve for y, so we divide both sides by x squared. So when we divide the first term by x squared, we're left with 3 halves. We divide c by x squared. I'm going to rewrite that as c times x to the negative 2. And that is it. All right. New page. Number 5. So for 5, let's see what we've got here. Dy dx plus y equals e to the 3x. Alright, so this looks like the correct format. We have a 1 in front of here. Our p of x is actually 1, and then the right side is a function of x. So we look like we're in business. We can go straight to integrating factor, e to the integral of 1 dx, which is just e to the x, and I multiply both sides by that. Now I will point out on the left-hand side, again, I'm just going to kind of skip and just go straight to what I know it's going to be. But on the right-hand side, I do have to multiply e to the 3x times e to the x. So I'm going to add those exponents. So I get e to the 4x. And now we integrate. So left-hand side is just this product, and then the right-hand side, we have to integrate e to the 4x dx. That is an integral that I would expect you can do. We'll get a 1/4 out here, e to the 4x plus c, and now divide through by e to the x. So when I divide through by e to the x, I get 1/4, and then plus, and then I'm going to have c e to the negative x, again bringing that e to the x from the denominator up to the numerator, and that should do it. This is number 5, and we look, hold on a second, what am I missing here? Oh, you know what I did? Oops. I got ahead of myself here. Let me get rid of this line. I made a mistake. Divide by e to the x, divide by e to the x, divide by e to the x. Okay, so this first one, these two, you subtract, right? 4x minus x, that's 3x. So we get 1/4 e to the 3x plus c e to the negative x. Okay, my fault. Going a little too fast. Let's slow down. Slow down. All right, let's look at number 6. Wait, was that 6? No, that was 5. Okay, let's look at 6. For number 6, we have dy dx equals y plus e to the x. Now, this is not in the correct form because I've got to get that y term on the left-hand side. So I subtracted on both sides. I can leave the e to the x on the right because it's a function of x. And then I have negative 1 as my p of x. Everything else looks fine. So my integrating factor will be e to the integral of negative 1 dx, which is just e to the negative x. And we multiply both sides by that. We know the left-hand side will be the derivative of the product of our integrating factor and y. And our right-hand side, when we put these together, look at that. You add those exponents and you get 0, so e to the 0 is 1. All right, integrate both sides with respect to x. And now divide both sides by e to the negative x. So I'm doing this over e to the negative x plus c over e to the negative x. We can bring those up. So we get x e to the x plus c e to the x. And that's it. This is our general solution. Y equals that. Working on 7 now. Right, a little different notation here. Y prime plus 3x squared y equals x squared. All right, so on this, we've got the correct format. Remember, y prime is really dy dx. We've got some function in front of y, some function of x in front of y, and then some other function of x here. So we're good to go. Integrating factor will be e to the integral of 3x squared dx. That's a pretty straightforward antiderivative, just x cubed. And so that's our integrating factor. So I know my left-hand side becomes d dx of e to the x cubed times y equals, be careful here, x squared times e to the x cubed. All right, we have to multiply both sides by that integrating factor. Now, left-hand side, when I take the antiderivative, is just the product. But the right-hand side, I actually have to figure out this antiderivative. And for that, I'll do it over here. Integral x squared e to the x cubed dx. Make a basic u substitution here. I'm going to let u be equal to x cubed. And the reason I'm doing that is because I know the derivative of that is 3x squared dx. And I kind of have that. I have an x squared dx. So if I just scale this by a third, I can get the expression x squared dx that I'm looking at up here, and then just rewrite this integral. So we have integral the x squared dx becomes 1/3 du. I'll put the du in the back, and then this piece here, e to the x cubed, becomes e to the u. And now that antiderivative is easy. 1/3 e to the u plus c, and then I'll just replace u with x cubed. So we're back here now. We have, I'm at the bottom of the page. We have e to the x cubed times y is equal to 1/3 e to the x cubed plus c, and then I'll divide everything by e to the x cubed, which will leave me a 1/3 on the first term, and then on the second one I'm dividing c by e to the x cubed, which will become c times e to the negative x cubed. I'm just bringing that up. We've kind of done this a couple of times now, so. All right, so that's it for number 7. Let me do I'm trying to get through number 12 here before I have to go. Let's look at number 8. All right, so for number 8, we have y prime again, plus 2xy. Everything looks good. X cubed. All right, so we're ready to go. Our p of x is 2x, so the integrating factor will be e to the integral of 2x dx. That's just e to the x squared. Multiply both sides by that, so we know the left-hand side becomes d dx of e to the x squared times y equals, now remember we multiplied both sides by e to the x squared, so we have x cubed times e to the x squared. And now we integrate both sides. Left-hand side is e to the x squared times y equals integral x cubed e to the x squared dx. Alright, this problem is going to be a little bit tricky. Not too bad, but we're trying to figure out what the integral of x cubed e to the x squared dx is. So we're going to make an interesting observation here that this could be rewritten as x times x squared e to the x squared dx. And if we do that and make the substitution u as x squared, then du is 2x dx, and we have x dx, we have x dx. The x squared here and the x squared here can be replaced with u, so we've got that. We're just off by 2 here, so if I multiply both sides or scale by half, we get that. So now I can rewrite this problem. This integral becomes, let's see, that x dx became 1/2 du, 1/2, put the du in the back. And then this x squared becomes a u, and then the e to the x squared becomes e to the u. So now it's gotten better, but we're not quite there yet. We have to do another substitution. So let me do another substitution. I'm going to say v is equal, oh, you know what? No, that won't work. We need to do integration by parts. So when we do integration by parts, you know, normally you're taught to use like u and v, but we're already using u here, so I guess what I'm getting at is integration by parts says that when you have integral of u times dv, that equals u times v minus the integral of v du. Okay, so that's the integration by parts formula. But since we're already using u in here, we're going to have to replace this maybe with like w, replace this with, come on, w, and then this will be like dw, something like that. So depending on how you're taught this, I'm going to do it the way I do it with a table. I think I'm going to have to move my table down here a little bit. So I'm going to use w here, dw here, and then dv here and v here. So we know w here will be u, this piece, and dv will be the e to the u du. So now what we do is we figure out what dw is, so we take derivative here, that's du, so I'm just moving down here. And then up here we're integrating, so the antiderivative e to the u is itself e to the u. So according to this formula, this integral, this integral here now becomes, I'm using this formula off of my table I made, will be w, which is u, times v, which is e to the u, minus integral of v, which is e to the u, and then dw, which is du. And that we can work out because that integral here is easier. So we get u e to the u minus just e to the u plus c. And then we replace all our u's with x squared. Okay, so that's all Cal 2 stuff. But let's get back up here. So we get e to the x squared y equals the antiderivative of that, which will be, remember u is x squared, e to the x squared minus e to the x squared plus some constant. All right, so that's just this right here with all my u's replaced with x squared. All right, let's get all this crap out of here. All right, so now what we'll do is we'll divide both sides by e to the x squared, so we get y equals x squared, that e to the x squared is gone, minus this e to the x squared is gone, so we get 1. Then plus, we're dividing c by e to the x squared, so I'm going to write c times e to the negative x squared. And that should be our solution. Oh, you know what? I forgot the 1/2. Crap. This 1/2 was out here. Forgot about it. So I'm just going to scale everything by a half. Half. This will be a half. And then the c, you don't have to worry about the c being scaled by a half because half of c is still a constant. So, okay. Sorry about that half. All right. Now number, where are we at? 9. Okay, number 9. So x squared y prime, that's already a problem, plus xy equals 1. So we do not want that x squared up front, so we got to divide everything by x squared. Plus 1 over x times y equals 1 over x squared. All right, so we divided everything by x squared, and now this looks like the correct format, and our p of x is 1 over x, so we need the integrating factor, which will be e to the integral of 1 over x dx, which is just e to the natural log of the absolute value of x, which is equal to just absolute value of x. So assuming that x is positive here, greater than 0, then which one are we working on? Yeah. So assuming that x is greater than 0, we can proceed to make this just x. So if x is greater than 0, okay. Then now what we can do is come back over here and multiply both sides by the integrating factor. So we know the left side becomes d dx of x times y. That's pretty clean. And then the right hand side, we just multiplied this side by x. So we just get 1 over x. And then we integrate both sides. So we get x times y equals integral of 1 over x dx. So xy equals natural log of the absolute value of x, but we're assuming x is greater than 0, so just natural log of x plus some constant, and then we divide both sides by x. So we get natural log x over x plus cx to the negative 1, again bringing that x on the bottom up, and this should be our general solution. Let me just check it. Everything looks good, and we are good. This is a valid solution so long as x is greater than 0. All right, number 10. Number 10, we have y prime, y prime equals 2y plus x squared plus 5. All right, so I got to get this in the right form. So why don't we bring that 2y over, and we can leave x squared plus 5 here because that is all just some function of x. And now we find our integrating factor, which will be e to the integral of negative 2 dx, which is going to be e to the negative 2x. Multiply both sides by that, so we know the left side becomes the derivative of the product of our integrating factor and y. And then equals, now this is going to be a little ugly, but it's the right hand side, okay, times e to negative 2x, like that. Oh my goodness, this is going to be not fun. Okay, integrating both sides. Left side's easy. Right side, we've got work to do. All right, so to do that integral, We're going to need integration by parts a couple of times. So let's do this first. This is equal to, this right-hand side is equal to x squared e to the negative 2x dx plus 5 times the integral of e to the negative 2x dx. So this second integral right here we can do without doing any real work. We have a little bit of worry. We have to worry a little bit about constants, but that'll become minus 5/2 e to the negative 2x. So a little bit of chain rule there. We have to count for the negative 2, so we divide by negative 2, and that's why that positive changes to minus, and we should be good there. And then we have plus some constant, and I'll just leave that constant out and not worry about the constant when I'm doing this first integral. So that first integral, let's do it over here. Gotta do integral of x squared e to the negative 2x dx. So some integration by parts. I'm going to let u be equal to x squared. dv is e to the negative 2x dx. Sorry, it's getting a little sloppy. du will be just 2x dx. And v, careful here, is negative 1/2 e to the negative 2x. So we have to worry a little bit about the chain rule there. Let me try and get that x to be a little nicer. Okay, we got that. So that integral becomes ultraviolet. That's these two multiplied. So that's going to be negative 1/2 x squared e to the negative 2x minus the integral, and now we're going to be doing these two multiplied together. So those 2's cancel, but I still have a negative. So I'm going to bring the negative out and make this a plus. And then I'm going to have x e to the negative 2x dx. So our integral's gotten better, but it's still, we have to do another integration by parts. So do it again. Go a little slower, I'm not slower here, a little faster here. I'm going to put u is equal to x, du is dx. Okay, dv is the e part, so e to negative 2x dx. And then v must be negative 1/2 e to the negative 2x. So we have equals, I'm going to get this line out of here. Okay, so that equals negative 1/2 x squared e to the negative 2x, that's just this part, plus, now I'm doing some brackets. Okay, this integral here, which is, you know, our whole integration by parts. So this times this, so negative 1/2 x e to the negative 2x. God, come on. This computer's starting to slow down on me. And then minus integral, and let's see, we're gonna be doing these two multiplied. So that I already have a negative here, I can bring that as a plus. I have a half there, I can bring that half out. And all I have is e to the 2x, negative 2x dx. All right, that integral I can do. So this should become negative 1/2 x squared e to the negative 2x minus 1/2 x e to the negative 2x, and then this last one I'm going to do my antiderivative of this, which is negative 1/2 e to the negative 2x, put it together with that 1/2 that was in front, so negative 1/4 e to the negative 2x, plus some constant, but I've already accounted for that constant. Oh my goodness. Okay, so back over here we had e to the negative 2x times y equals, and now the part we just found, which was negative 1/2 x squared e to the negative 2x minus 1/2 x e to the negative 2x minus 1/4 e to the negative 2x, and then we have this part right here. Oh my goodness. Minus. Now we need y by itself. We divide everything by e to the negative 2x. So we get y equals, okay, this is going to be gone, that's going to be gone, that's going to be gone, that's going to be gone. So we get negative 1/2 x squared minus 1/2 x minus 1/4 minus 5/2. What else? Plus a constant over e to the negative 2x, so it's going to be the constant times e to the positive 2x. And these two right here can come together. That's minus 6/2, or sorry, no, I need a common denominator. So 4 here, 10 here, so minus 11/4. So all of that's going to come minus 11/4. Come on, erase. Minus 11/4. Alright, let's see, let's check this bad boy. Negative 1/2 x squared minus 1/2 x minus 11/4 plus c times e to the 2x. There we go. Alright, that is your general solution. That problem was a little more involved, would you agree? Alright, I'm going to stop and come back and do a little more later. Going to be working number 11 here. Let's see. And make sure I'm on number 11. Yeah, okay. Okay, so number 11, we have parentheses x plus 4y squared, and we've got dy plus 2y dx equals 0. So if we wanted to get this of our standard form, where we've got something like y prime plus some function of x times y equals some other function of x, then we need to get this y prime, so we need to divide through by dx. So let's see what happens when we do that. We're going to get this will become, when we divide that by dx, we'll get our y prime there, and then plus 2y, and then equals 0 divided by dx, still 0. So that should do it. And now what we notice here is a little bit of a problem, because when we look at this first coefficient here, or in front of this factor in front of y prime, that is supposed to be a 1, so we have to divide through by it. But the problem is that we need to have p of x, a function of x only, and then y by itself. We have y by itself. When we divide through by this, we're actually going to have a y in there, and we need it to be just a function of x. So that's not going to work. So instead, what we're going to do is something we haven't done, is we're going to kind of revamp this formula and say, this formula would also be the same if we just change the places of x and y. So instead of doing y prime, what if we have x prime plus some function of y times, instead of y, x, then equals some function of y. If we look at it that way, then our integrating factor will be e to the integral of p of y dy. So we're doing everything in terms of y instead of x. So let's try that. Let's try and get an x prime. So we're going to divide everything through by, sorry, I did that wrong. Yeah, dy. Divide this through by dy. This will give us our x prime. So what we'll have is this. We'll have x plus 4y squared, the dy is gone, plus 2y x prime, and then equals 0. And now what we try and do is make it look like this here. So let's get a coefficient of 1 in front of x prime. So let's divide everything by 2y. So we take this divided by 2y, this divided by 2y, this divided by 2y, this divided by 2y. Then we will have, let's see here, watch the way I write this. I'm going to write this first one as 1 over 2y times x, and then plus we'll have 2y, and then we'll have plus x prime equals 0. Now we're getting closer. What we needed was x prime, right? So we have x prime. We need some function of y in front of x. So here we go. There's some function of y in front of x. And then on the other side of the equation, we need just some function of y, so we can take this 2y and move it over to the other side. So let's go ahead and do that. Rewrite this. X prime plus 1 over 2y times x equals negative 2y. And now we have it looking the way we need it. So now what I'm going to do is find an integrating factor. To do that, I do e, what was that? E raised to the integral of our function of y, which is in front of x, so 1 over 2y, I'm going to write that 1/2 times 1 over y dy. Okay, so the antiderivative of that is just going to be natural log of the absolute value of y, so e to the 1/2 natural log of the absolute value of y. So long as y is greater than 0, we can get rid of that absolute value and bring the 1/2 up. And raising y to the 1/2 is the same as the square root. So we get e to the natural log of the square root of y, so long as y is greater than 0. And then the e and natural log go away, so you just get square root of y. So the same thing we did before. We're going to now take this equation and we're going to multiply both sides. Now I haven't been showing this step, but we're going to multiply both sides by square root of y, square root of y. And then on the left-hand side, we already know that this is going to turn into the derivative of a product, but it's going to be the derivative with respect to y this time of the integrating factor, which is square root of y, and instead of times y, we do times x. So same thing, you can check for yourself that if you take derivative of that product with respect to y, you would get this thing up here if we distributed that square root of y through. And on the right hand, we have negative 2y to the 3/2, just using properties of exponents. Now we integrate with respect to y to get rid of this dy, and then integrate this side with respect to y. So the left side becomes root y times x equals, okay, negative 2 times, we have to do the antiderivative of y to the 3/2. That's just a power rule. So we're going to get 2/5 y to the 5/2 plus c. And now instead of solving for y, we're going to solve for x. So basically we're doing the whole problem, just kind of switching our variables around. So we have x equals, dividing through by square root of y. So I'll have negative 4/5. And then when you take this and divide it by square root of y, it's the same as dividing through by y to the 1/2. So you subtract 5/2 minus 1/2 is 4/2, which is 2. So y squared, and then plus, we're dividing also the c by this. So I'm just going to rewrite that as c times y to the negative 1/2. All right, and that should be it. Let me just double check it. Yep, it looks good. So that is our general solution. It's actually a function of y. X is a function of y, and it's only valid if, I don't know why it keeps doing that. That is weird. It has not been doing that. So that's only valid if y is greater than 0. All right, let's look at number 12. So for 12, we have dx dy equals x plus y. In other words, x prime equals x plus y. So we're going to be using the same idea here. X prime plus some function of y times x is equal to some other function of y. So I'm just going to start moving things around here. I have x prime minus x equals y. And so you can see we match up real good. The thing to note is that this p of y here, it's a constant. It's actually negative 1. in front of the x, and then our function of y on the other side, you know, here is just y. Okay, so we're ready to go here. We need an integrating factor, so we go e to the integral of -1 with respect to y, and that's just e to the -y. Okay, so now we multiply both sides by that, and I will start going shortcut again. I'm just going to get right to it. The left side we know is d dy, not dx, and it is our integrating factor times x, right? And then equals the right-hand side, y times our integrating factor. And then now we're going to integrate this with respect to y on both sides. So when we do that, the left-hand side is e to the -y times x equals, now we need to do this integral with respect to y. I said it, but I didn't write it. So I'll do that over here on this side here. We will have integral y e to the -y dy, and that I'll use integration by parts. So I'm going to start going a lot shorter, I think, on this, assuming that you are comfortable with integration by parts. I'm going to put, you know, this is what I'm going to use for u, this is what I'm going to use for dv. And then we differentiate down, so dy, we integrate up. This is -e to the -y. Be careful with that, that chain rule on that. So now we rewrite it. This integral becomes these two multiplied, okay, which is going to be -y e to the -y, and then minus the integral of these two multiplied, and that had a negative sign, so I'm going to just make this positive and then have e to the -y dy. And now when we integrate that, we get another negative out, so -e to the -y plus c. Okay, so this right-hand side is -y e to the -y minus e to the -y plus c. And we're going to solve this for x. So we're going to go ahead and divide through by e to the -y. So x will be equal to, when we divide that here, and here, and here, and here, oop, that's a negative, then we get cancel, cancel, or reduce, if you want to say reduce, that's probably better. -y minus 1, and then plus, and then c over that is the same as c times e to the +y. And that should be our answer for 12. Let me just double check. Yeah, everything looks good. All right. Try something here. Okay, moving on to 13 here. 13. Okay, x dy equals parentheses x sine x minus y dx. All right, so this is, we kind of have that to make that choice, you know, do we want it to do the standard way, or do we want to try and do it where we're solving for x at the very end? And let me just try the standard way. I'm going to divide both sides by dx. So when I divide this by dx, I get y prime. So x, y prime, and then equals, and when I divide the right-hand side by dx, I get x sine x minus y. So I think I'm going to be able to get this like the first way. I'm going to go ahead and bring this y over, because I need a y on that side, and then the right-hand side will just be a function of x. So that seems okay. And then on this side, I need to divide everything by x, so I get a coefficient of 1 on the y prime. And when I do that, watch, I'm going to write this as 1 over x times y. So there's my function of x, my p of x in front of y. When I divide the right-hand side by x, I just get sine x. So everything works out pretty nice there. And now I need my integrating factor, which will be e to the integral of 1 over x dx, which is just e to the natural log of the absolute value of x. And so long as x is greater than 0, this is just going to be e to the natural log of x, which is just x. So our integrating factor is x. So my left-hand side becomes the derivative of a product. It's my integrating factor times y. And then my right-hand side is sine x times my integrating factor. So I'm going to write x sine x. All right, and now we will integrate both sides with respect to x. Left-hand side is just the product, x times y. And the right-hand side is this integral, which we're going to need to do something to. So over here, we've got integral x sine x dx. Again, integration by parts. I'm going to let x be here, sine x dx here. Okay, derivative of x is dx. The antiderivative of sine x is negative cosine x. And so this becomes negative x cosine x, multiplying the top two across, and then minus the integral, and then I'm going to multiply these two, bring the negative out, make it positive. This will just be cosine x dx. And so I get negative x cosine x, and then antiderivative of cosine x is just sine x, and then plus some constant. So we have x times y equals negative x cosine x plus sine x plus c. Divide everything by x to get y by itself, so we get negative cosine x plus sine x over x plus c over x, or you could write c times x to the negative 1, however you want to write that. And that, I believe, is number 13? Yeah, number 13. Let me double check it. All looks good. Oh yeah, and then also remember this is valid for x greater than 0. All right, moving on. 14. All right, so for 14, we have 1 plus x squared dy plus xy plus x cubed plus x dx. That looks complicated. Equals 0. All right, let's divide everything through by dx. I've done this several times, so that's just going to become y prime there. Plus, and now this, you don't need the parentheses anymore because the dx is gone. And now the question is, can I move things around properly here? And it looks like I can. Looks like I can leave this here for now. And then leave the x times y here. And then make that equal to negative x cubed minus x. So move those x terms here to the right-hand side. So we have a function of x on the right. Now what we need is a coefficient on y prime to be 1. So I divide through by 1 plus x squared. So y prime equals, I'm dividing out the 1 plus x squared. So on this, I don't know why I put equals. So plus, I'm going to have this x. I divide it through by 1 plus x squared. Times, I still have the y there, then equals, and notice on the right hand side that negative x cubed minus x is actually negative x times x squared plus 1. And we're going to divide that through by 1 plus x squared, which is the same as x squared plus 1, so that's going to just cancel out and you're just going to be left with negative x on the right hand side. So that's nice. And we've got the form we need, right? We've got everything. We've got our p of x here, we've got some function of x here, y prime in front, so we're all good to go. So integrating factor, e to the integral of x over 1 plus x squared dx. Okay, let's look at that integral real quick. I'm just going to do this right here real fast. This is a basic u substitution. If I let u be equal to 1 plus x squared, the derivative of that is 2x dx, which I have up top. Right, I've got it right here, those two things. So what I can do now is just scale this by a half. That'll give me x dx exactly. So that integral now becomes, let's see, integral 1 over 1 plus x squared becomes our u, then the x dx becomes 1/2 du. So this is 1/2 integral of 1 over u du, which is the natural log of the absolute value of u. which is 1/2 natural log of 1 plus x squared, absolute value. But I don't need to look at the absolute value because 1 plus x squared is always going to be a positive number, so I don't have any domain issues here. And now we can go back up here and say this is e to the natural log of the square root of 1 plus x squared. So all I'm doing there is just taking that property, pushing the half up here, taking the square root, and the e and the natural log cancel out. So at the end of the day, our integrating factor is square root of 1 plus x squared. That's our integrating factor. So back to the problem, I know that my left-hand side is going to turn into the derivative with respect to x of the product of my integrating factor times y, and that must equal, now be careful here on the right side, negative x times my integrating factor. There it is. All right, time to integrate that with respect to x. So when I integrate the left-hand side, I get square root 1 plus x squared times y equals integral, I'm going to pull the negative out, of x root 1 plus x squared dx. Okay, so I need to do that integral. And let me see, I'm not out of room yet. Okay, good. So on the side here, that integral of x square root of 1 plus x squared is another basic u substitution. U is equal to 1 plus x squared. Du is 2x dx. And 1/2 du is going to be x dx. And I'm just using the fact that I have x dx right there. So when I rewrite this integral, I'll have square root of u times half du, and then that's 1/2 integral of u to the half du, and then the antiderivative of that is going to be 1/2 times 2/3 u to the 3/2 plus some constant, and then remember u is actually 1 plus x squared. These twos will cancel. So we should get back over here, square root of 1 plus x squared times y equals, now remember we had a negative in front of all this, so negative 1/3, and then u, which is 1 plus x squared to the 3/2, and then plus some constant. Now, we don't have to worry about the negative going through and distributing to that constant because multiplying constant by a negative is still a constant, so we don't know what the number is. It's not really relevant. So there's where we are, and now we divide through by the square root of 1 plus x squared, which remember is just 1 plus x squared to the half. So we're divided on the left side, we just get y, oops, not y prime, not y prime, equals negative 1/3. So when we take this and you divide that by this, you subtract, and so you're just going to get 1 plus x squared to the first power, 2/2. So you're just going to have 1 plus x squared there, and then plus, now we have to take our constant and divide it by the square root of 1 plus x squared. And that should be it for number, what is this, 14? Check it real quick. 1/3, blah, 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 yeah, okay. Okay, so that's number 14. Let's take a look at number 15. One plus e to the x times dy dx, which is y prime, plus e to the x times y equals 0. All right, so this almost is almost in the form we need. We just need to get rid of this 1 plus e to the x. So I'm going to divide everything by that. So y prime plus e to the x over 1 plus e to the x times y prime, and then fortunately for us, the right side is still 0. So we've got our integrating factor. We're going to create our integrating factor there. We're going to do e to the integral of e to the x over 1 plus e to the x dx. And that's that integral right there. I'm just going to show you. Yeah, I should just do it. Integral of e to the x over 1 plus e to the x dx. Make a substitution. Use 1 plus e to the x. The derivative of that is just e to the x dx, and we have e to the x dx right there on top. So this turns an integral of 1 over u times exactly e to the x dx, which is just du. So the antiderivative of that is natural log of the absolute value of u plus some constant, which is natural log of 1 plus e to the x plus c. Now, 1 plus e to the x is always positive, because e to the x is always positive, and adding 1 is still positive, so we don't need the absolute value, and that means we can turn this into e natural log of 1 plus e to the x, and they're gone, and we get our integrating factor 1 plus e to the x. Now, that means we have the derivative with respect to x of our integrating factor 1 plus e to the x, k times y, equals, well, fortunately for us, the right-hand side is 0, so when we multiply that by the integrating factor, we still get 0. And that means we can integrate both sides with respect to x, and we just get 1 plus e to the x times y equals the antiderivative of 0, which is just some constant, and then pretty straightforward to solve for y there. Just divide both sides by 1 plus e to the x. And that should be it for number 15. Number 16. Still got a long way to go. Starting to question whether or not I really want to do all these problems. Okay, so this, and then we have dy dx, which is y prime, equals 3x squared y. All right, so yeah, we're going to make this look the way we need it. We're going to bring that factor on the right hand side over to the left and make it equal to 0. That way we have something in front of y. And now we will divide through by 1 minus x cubed. So everything gets divided through by 1 minus x cubed. And then we have, you know what I'm doing? I'm changing this to a plus and put the minus up here, because I can already see that the derivative of the bottom is the top there, so that's going to work out real nice. Equals 0. Okay, so go get our integrating factor now. So e to the integral of negative 3x squared over 1 minus x cubed dx. If we do this integral on the side, okay, I'm just going to do this on the side here. If we let u be equal to 1 minus x cubed, then du is exactly negative 3x squared, which is exactly the top, dx, which is exactly these two things. So we really just get like integral of 1 over u du. And we already know that that's just the natural log of the absolute value of u plus a constant. And u here is 1 minus x cubed. All right? So since we're dealing with something here, let me check. Yeah, so since we're dealing with that, we've got to make sure that 1 minus x cubed is always going to be positive. So, and there's different ways to, oh God, I don't know why it does that. There's different ways to look at this. One way would just be look at that as a function. You know, that's just the, like a graph. That's just this x cubed function, but it's reflected because it's negative, so it's like that, right? It's negative x cubed, and then you're adding 1 to it. So when you add 1, hold on, what's going on here? 1 minus x cubed, yeah, that's right. Yeah, so when you're, I don't know why I'm looking here at the solution here. Why are they saying x is between 1 and infinity? I don't agree with that. Boom, 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 boom. Boom, 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 boom. Well, yeah, okay, so if x is bigger than 1, yeah, that's a little bit of a problem. Let's just not worry about that right now, the domain. I'm going to have to double check on the solution here to see what's going on. But let's just continue and say that we've got the correct domain restriction on that, and just assume that we can drop the absolute value. So we'll have e to the natural log of 1 minus x cubed, and then they'll cancel and we'll just get 1 minus x cubed here. All right, so that's an integrating factor. We know the left-hand side will become d dx, the derivative of an integrating factor times y, and then equals, again, 0. So this is going to turn out to be real nice. 1 minus x cubed times y, integrating with respect to x, equals a constant. So y is equal to that constant divided by 1 minus x cubed, solving for y. Okay, so I'm looking, I mean, it's the correct answer. The book is saying that x has to be between 1 and infinity, which, you know, we do have a little bit of a problem there. That, you know, if let's say x is 2, and we were to plug it in here, it wouldn't be defined, right? The natural log wouldn't be defined, so to me it's looking more like x has to be between -1 and 1. No, 0 and 1. Because it's cubed, we can still get negative there. So like 0 and 1. 0, if we're at 0, we get 1, so that'd be okay. We could have it be 0, and if we can't plug in 1. So to me, it's something like that. But I'll double check, and if I'm messing something up, then I'll correct it. Let's move on. All right, 17. Actually, I'm going to just cut it out here and come back. Okay, I went and double checked this, and this is correct. Let me see here. This is not correct. For the answer that we have here, they did something, they factored out a negative, and that kind of changed things a little bit, but no worries. No worries, we're good to go. I just need to make a slight adjustment on this domain. We can have that our x has to be less than 1, but it can also be less than 0, because if I put a negative in here and cube it, then I'm still going to subtract it. So basically this can be negative infinity less than x less than 1. Okay. All right, we're moving on. 17. All right, we've got cosine x dy dx, so y prime, plus y sine x equals 1. Okay, so I'm going to try and get y prime by itself, so divide through, we're going to get y prime, divide through by cosine, plus we're going to have sine x over cosine x, which is going to be tangent x, and then times y, and then equals, I divided by cosine, so 1 over cosine is secant. All right, so that looks like our equation. We'll work with that, and we'll find the integrating factor. So if we do e raised to the integral of tan x dx, this is e raised to the natural log. So this is a formula. These are located in the back of the book, and if you don't have these readily available from Cal 2, this is in the table of integrals in the back of the book. Let me see what formula it is. Where is it? Where the heck is it? Oh, there it is. Formula number 12. So this turns out to be negative natural log of cosine x. All right, and now we'll move that negative up top. So e to the natural log of cosine x to negative 1 is not the inverse cosine, it's 1 over cosine, so that's actually absolute value of secant of x. And this is only going to work, okay, so this right here is only going to be valid when cosine is positive. So if we look at the unit circle, cosine is only positive when we're here in the first or fourth quadrant. So our x would have to be restricted between pi over 2 and negative pi over 2 for this to be valid, for us to be able to drop that absolute value. So these will cancel, the absolute value will drop, and we'll just get secant x. Okay, so that's our integrating factor. Now we come over here, we know that this is going to be d dx of our integrating factor secant x times y, and then equals, we have to multiply secant x by secant x, so it's secant squared x, and that's nice because when we integrate that with respect to x, the antiderivative of secant squared x is just tangent x plus c, and then we divide everything through by secant x. So tangent x divided by secant x is the same as multiplying by cosine x, then plus c over secant x, which is the same as multiplying by cosine x. So I'm just going to go c times cosine x. And let's see, tangent is sine over cosine, so this is sine x over cosine x, and the cosines cancel, so we just get sine x plus c times cosine x. And that should be our general solution here, so long as x is there. All right, moving on. 18. All right, dy dx, so y prime plus, I'm going to rewrite it backwards. Let's see, cotangent x times y equals 2 cosine x. All right, I think we're ready to go. There's nothing else for us to mess with here. So e to the integral of cotangent x dx, which is e. Now again, this is going to be a reference thing. I'm going to go to formula 13. That's natural log of sine x is the antiderivative. This is only valid when sine is positive. So sine is only positive when you're between 0 and pi. Oh, that's wrong. 0 and pi. And then we can drop the absolute value in the e, and the natural log go away, so we just get sine x. So we have d dx is our integrating factor sine x times y, and then equals, on the right hand side we have to multiply this by sine x. Now we integrate, so the left hand side is just this, and the right hand side we need to integrate. I'll pull the 2 out. Cosine x sine x dx. Basic u substitution, u is sine x, du is cosine x dx, and that means that that integral is really just like, there's a 2 in front, it's really just like u du. And so the antiderivative of that is 1/2 u squared, but the 1/2 and 2 cancel, so you just get u squared plus c. So at the end of this, you're just going to get sine squared x plus c. This side is sine x times y. Divide everything through by sine. And c over sine is the same as c times cosecant x. So for number 18, sine x plus c times cosecant x, that's only valid when x is between 0 and pi. 19. All right, x dy dx, which is y prime, plus 4y equals x cubed minus x. Okay, everything looks good. Oh no, it's not good yet. Got to divide through by x. So when I divide the right side by x, both terms get reduced down by one power, or one factor. Okay, so integrating factor, e to the integral of 4 over x, so that's 4 times 1 over x dx. That's going to be e to the 4 times natural log of the absolute value of x. Bring the 4 up. E to the natural log of x to the 4th. Don't need the absolute value anymore because we're going to be raising x to the 4th power. These cancel, so just x to the 4th. So d dx, x to the 4th times y, equals, now multiply the right hand side by x to the 4th, and now I integrate. Okay, when I take the antiderivative of this, it's 1/7 x to the 7th minus 1/5 x to the 5th plus c. And now I divide everything by x to the 4th. So 1/7 x cubed minus 1/5 x squared plus c times x to the negative 4. Oh, getting a call. Let's see if I can pause this. Okay, I should be back here. Number 19. Double checking here. Okay, let's move on. Working number 20. So we've got 1 plus x y prime minus xy equals x plus x squared. Alright, so we've almost got what we need here. We just need to divide out the 1 plus x through everything. That'll leave us with y prime minus x over 1 plus x y times y equals, now we divide the right side by 1 plus x, but just keep in mind this is actually x factored out 1 plus x. So when we divide that by 1 plus x, we're just going to get x on the right hand side. Alright, so now we need to go ahead and get our integrating factor. So we want to do e to the integral of, be real careful, we have a negative there. So I'm going to put that negative here, negative x over 1 plus x dx. And for that integration, I think what I'll do is long division first. There's several ways you could go about this, but I'm going to do it this way. And multiply by 1, that gives me x plus 1. Then I subtract this row, I get negative 1 here, so that leaves me with minus 1 over x plus 1. And so what we get here is e raised to, I'll leave the negative out for now. And I'm going to write 1 minus 1 over x plus 1 dx. And that is, I'm going to put the negative back in and switch the order. Okay, and then now integrate. So e to the natural log of x plus 1, absolute value of x plus 1 minus x. And this will only be valid if x plus 1 is greater than 0, which means x has to be greater than negative 1. So we have, so this is a little weird looking. I'm going to use a property of exponents to rewrite this as e to the natural log of x plus 1. I'm getting rid of the absolute value because I'm restricting our domain. Then over e to the x. So this expression is equivalent to this because if you do properties of exponents, e to that power over e to that power, you'd subtract those two, and that essentially takes you back here. So the good news about that is this top numerator becomes x plus 1, and the bottom is just e to the x. Okay, so now coming back over here, we know that the left-hand side is the derivative with respect to x of our integrating factor, x plus 1 over e to the x, times y, and then equals, we have to multiply the right-hand side by that integrating factor, so I'm just going to write it like this. Ooh, okay, now integrate both sides with respect to x. And the left-hand side becomes x plus 1 over e to the x times y, and then equals, now I've got to work on that integral. So I think I'll do that over here. Alright, so I'm trying to integrate x squared plus, I'll write it this way. X squared plus x, I distributed the x through the top, and then I'm going to bring the e up, so e to the negative x dx, and I'm going to have to run integration by parts on this probably twice. So the way I'm going to do this, I'm going to put x squared plus x here. The derivative of that's 2x plus 1. I'm going to put e to the negative x dx here. Sorry, that's a dx down there also. And then this will be negative e to the negative x. So through integration by parts, I have that this integral is equal to negative x squared plus x times e to the negative x. That's multiplying those two. And now got to do these two in an integral and subtract, but I already have a minus there with the e, so it's going to become plus integral 2x plus 1 times e to the negative x dx. So I've kind of reduced that quadratic down to a linear, and now I'm going to do integration by parts again. 2x plus 1, and derivative of that's just 2 dx. Got e to the negative x dx here. I'm going to integrate negative e to the negative x. And so this integral here is going to become something. We still have this stuff out front. So that part right there becomes negative 2x plus 1 e to the negative x, and then that minus there, it's going to turn to a plus again, and then I'm also going to have a 2 out here, and then e to the negative x. And let me go ahead and integrate that last piece. So minus 2, minus 2x plus 1 times e to the negative x, and then minus 2e to the negative x plus c. And then I still have this stuff in front. So let me see. I'll try and rewrite what's up here. I had integrated the left side, so I've got the x plus 1 over e to the x times y equals now negative x squared plus x times e to the negative x minus 2x plus 1 times e to the negative x, and then minus 2e to the negative x plus c. Alright, so that's everything over here filled in. And what now? I have to divide everything through. And let me also point out that on the left-hand side, this e to the x on the bottom is really like an e to the negative x here. So let me get rid of those first. I divide that out here, it's gone. Divide it 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 here. And that turns into e to the positive x when I divide by e to the negative x. So I have that, and then I have to divide everything through by x plus 1. So here's where we'll be at. We'll have y equals, now when I take this, which is really x times x plus 1, and then there's a negative out front, when I divide that by x plus 1, I just get negative x. So I'm going to have negative x minus 2x plus 1 over x plus 1. And then I have minus 2 over x plus 1, that's dividing that there. And then plus c times e to the x, and I still have to divide that by x plus 1. Alright, and I think we can put these two together. They have the same denominator. And let's keep in mind that negative will go here, and negative will go here, and then I had a negative there, so we should just get negative x, and then how do I want to write this? I'll do plus negative 2x minus 3 over the common denominator. And then plus c times e to the x over x plus 1. And I guess we could put those together too, but I'm going to leave them just like that. Let me just check to make sure this looks good. 20. Yeah. Okay. Did we talk about domain? We did. That was way up here. Yeah. So our domain on this one is that x had to be bigger than -1. All right. That was kind of interesting. All right. 21. Okay. X squared y prime plus x times x plus 2 y equals e to the x. So I'll have to divide everything by x squared first to get the y prime by itself. Oh, I've done that several times. So when I divide this x times x plus 2 divided by x squared, I just get one more x in the denominator. And then on the right side, divide by x squared. All right, there we go. Integrating factor, e to the integral of x plus 2 over x dx, which is the same as, because I have two terms in the numerator, one denominator, I can do x over x, which is 1, plus 2 over x dx. That'll be easier to integrate. So e to the x plus 2 natural log of the absolute value of x, which becomes e to the x plus natural log of x squared, as long as x is bigger than 0, because this is only defined if x is bigger than 0. So, and now I'm going to use properties of logs again, or properties of exponents again, like that, rewriting that way, and then now this right here just becomes x squared. So I'm going to write x squared e to the x. That's our integrating factor, so d dx should be that integrating factor times y equals, and then when I multiply this side by x squared e to the x squareds are gone, and I just get e to the 2x. Now integrate both sides, so x squared e to the x times y equals, the antiderivative of that should be 1/2 e to the 2x plus c, and divide through by x squared e to the x. So y equals, let's see what happens here. I'm going to have, I won't do the 1. I should just have e to the x, because when I come in here and I do x squared e to the x, these two, we subtract the exponent, is 2x minus x is just x. And so on the bottom I still have a 2 and I still have an x squared, and then plus c over x squared times e to the x. And that should be it within our domain restriction. This is number 21. Yeah, they write it a little different, but it's the same thing. Okay, moving along. Number 22. 22, xy prime plus 1 plus x y equals e to the negative x sine 2x. All right. First I'll divide by x. Boy, this looks real nasty on the right side. Okay, hopefully that'll clean up. All right, integrating factor e to the integral of this guy right here. That's really 1 plus 1 over x, split it up. And that's going to be e to the x plus the natural log of x, as long as x is bigger than 0. And then that's going to be e to the x times e to the natural log x, which is just x e to the x. Okay. Well, it's actually not too bad. We know the left side is going to be d dx of my integrating factor x e to the x times y equals, now when I multiply this side by x e to the x's cancel, and then this guy and this guy are going to cancel out. And so all I'm left with is sine 2x, and that's good because I can integrate that. So take the antiderivative with respect to x on the left side, and then on the right side, let's see, we should get 1/2 cosine 2x plus some constant. And yeah, that's it. So now we will divide through by x e to the x. So I'm going to have cosine 2x over 2x e to the x, and then plus c over x e to the x. And that should be it for number 22. Where's my negative? Oh, yeah, the antiderivative. Stupid me. The antiderivative, I'm missing the negative. You're probably sitting there going, where's your negative? There it is. I messed that up. Okay. And then, yeah, okay, everything else looks good. In the solutions in the book, they actually start at some point leaving the answers like this and not even solving for y. So we'll see how it goes. We might wind up starting to leave things. Number 22. Wait a minute. I did 22, didn't I? Let me see. Yeah, I did 22. You probably don't realize it, but I actually paused the video and come back and lose track of things. I'm not quite sure how it's going to turn out on the video, but I do pause every once in a while and stop it sometimes also, and then come back later and do it. So, all right, just writing this down. It's cosine cubed x minus 1. Ugh, this looks nasty. Okay, yuck. Well, I'm going to shoot for y prime here, so I'm going to divide by dx, so this will give me cosine squared x sine x. Let's go for this. Dy over dx is y prime plus y cosine cubed x minus 1, don't need the dx anymore, equals 0. That looks good. I've got function of x. I've got a y by itself with a function of x. Move the 1 over. Let me move the 1 over. And now I need to divide everything by cosine squared x sine x. So y prime plus. Okay, when I divide this by cosine squared x sine x, I'm left with a cosine x on top and a sine x on the bottom, which will be cotangent. Then I still have the y. On the right side, I've got 1 over, and I've divided through by cosine squared x sine x. That's kind of ugly. Let's go with this. All right, so integrating factor, e to the integral of cosine x over sine x dx. Now that one is just a basic u sub, or you can turn it into cotangent. Look at the formula in the back of the book, but the u sub is just this. So you can see that we have everything we need there. That's just going to turn into like 1 over u du. So natural log absolute value of u. So this is going to be e to the natural log of the absolute value of sine x. And sine is only positive if x is between 0 and pi. So this is restricting. And then the e and natural log go away. We'll just get sine x. Okay, that's our integrating factor. So now we have left side is d dx of sine x times y, and then multiplying this guy right here by sine x. That's good. We get 1 over cosine squared. Nice. That's secant squared x. I don't have any issues integrating that. That's just tangent x plus c, and then divide everything by sine. Let's see, sine x over cosine x, and I'm dividing that by sine, which is the same as multiplying by the reciprocal, and then plus c over sine x. So we should just get secant x plus c times whoa. Sometimes I wonder how that happens. Okay, times cosecant x. All right, this is number 23. Secant x. Yep. Wait a minute. Sine. Why did I say I was going to do every problem? Oh my goodness. All right. 1 minus cosine x dy plus, all right, 2y sine x minus tangent x dx equals 0. Yuck. Let's go with y prime. So divide everything by dx. That term right there has everything I need. And then the other one, the tangent x, I moved to the other side. So that falls into the form. Let's divide through by 1 minus cosine x. So 2 sine x over 1 minus cosine x y times y equals tangent x. Sorry, tangent x over tangent x over 1 minus cosine x. All right, integrating factor. Pull that 2 out. Sine x on top. 1 minus cosine x on the bottom. It's e raised to all that. So for that integral, basic u sub u is equal to the bottom. Derivative of that is just the top. That's really nice. So we just have like 1 over u du, so this is going to be 2 natural log of absolute value of u, which is going to be equal to 2 natural log of u is 1 minus cosine u, and that should be okay. Let me see. So what we need there is we need 1 minus cosine u to be bigger than 0. So cosine u less than 1. And that should work everywhere except at pi over 2. Everywhere at pi over 2. And yeah, so as we proceed through here, I'm going to start paying a little less attention to these details on the domain, just because we've got to get through these problems. Let me go ahead and bring the 2 up and then wipe out the e in natural log. So we're just going to get 1 minus cosine u, that quantity squared. All right. sorry, cosine x. I don't know why I put u there. No idea. That should be x, that should be x, that should be x. Alright, now we know the left side over here is going to become derivative of the product of 1 minus cosine x, that quantity squared, times y, equals, real nice here, when we multiply this right here by 1 minus cosine x squared, like one of them cancels here with that. So what we're left with is tangent to x times 1 minus cosine x. Now, integrate the left side, we get 1 minus cosine x squared times y equals, now we have to integrate this. Not quite sure how I want to do this. Let me do it this way. Integral, let's distribute here to here. So tangent x there, and then minus tangent times cosine, that's sine x over cosine x times cosine x. So that's just sine x dx. And we actually did a little while ago the antiderivative of tangent x. We found out that that was natural log of the absolute value of sine x. And then the antiderivative of sine x is cosine x with a positive there. And then plus c equals all this. Let me just take a look at that real quick. Did I? Oh, you know what? We didn't do this one earlier. We did another one. We did cotangent. This is not right. This is natural log of secant x. I'll let you do that. It's a formula, but it's also something that you can work out by hand. Yeah. Okay. I'm not going to solve for y. All right, 25 now. Okay, we're working number 25. I already started writing this down. Make sure I got all this. Okay, minus y e to the y dy equals 0. Okay, so let's see here. Which form do we want to get this into? Let's see, if we try and make, let's go for y prime, so I'll divide everything by dx. Let's just see what happens here. It would be y plus, and then everything here in parentheses, x, y, plus 2x minus y e to the y, and then we'll have y prime equals 0. And that, I think, is going to be a problem because when I try and get a coefficient of 1 in front of y prime, I'm going to be dividing through here by things that have both y and x in them. And that's not what I want. I just want things with x. So let me try instead to get it to be x prime. So I'm going to divide everything by dy. If I do that, I'm going to get y times x prime plus, and because this dy is gone, I just have everything that was in parentheses. And then equals 0. So again, my goal is to get x prime plus some function of y in front of x equals some other function of y. Something like that. So it looks like I can take this stuff here to the right side of the equation. Let me go ahead and cheat a little bit and just do that. Okay, so I've got a function of y on the right side. I need x prime by itself. I need to divide everything through by y. Let me do that. X prime plus just x, and then plus 2 over y times x, and then equals, when I divide the right side by y, I get e to the y. So that's looking good. Problem now is I'm trying to get some function of y just in front of x. I have two terms here with x. So what I'll do is I'll factor out an x. So I'll have x prime plus, when I factor out 1 plus 2 over y x, and then equals e to the y. And that looks like that's going to work. I have my function of y here in the front. Is going to be this guy right here. So now let's go ahead and get our integrating factor. So we've got to do e to the integral of that function of y, which is 1 plus 2 over y dy. And I can integrate that pretty easily. I'm going to get e to the y plus 2 natural log the absolute value of y. And then I can bring that 2 up. And then I'll have natural log of y squared. And for this, I'm just going to be looking at if y is greater than 0, so that we don't have any domain issues on this natural log right here. And we should be good to go here. So I multiply both sides by the integrating factor, and so my left side will now turn into the derivative with respect to y of my integrating factor, e to the y plus, you know what, like we did in the last problem, let me clean this up. This is really e to the y times e to the, oops, did it again, plus e to the natural log of y squared, which is just e to the y times y squared. And that's a little bit easier to work with. So e to the y times y squared times x, that's the derivative of that product, must equal, now the right side we have to multiply this by e to the y, so we get e to the 2y times y squared. So that's just hitting that with the integrating factor there. Okay, integration of this with respect to y on both sides. And the left side is just our e to the y times y squared times x. And then the right side is this integral. I'll just write it like this, y squared e to the 2y dy. That looks like that's going to be integration by parts a couple of times. Let me work that over here. Integral e y squared e to the 2y dy. Okay, integration by parts. So I'm going to put my y squared here, my e to the 2y dy here. That's going to be 2y dy here. And this is going to be 1/2 e to the 2y. And so that integral now becomes 1/2 y squared e to the 2y minus, let's see, the 2 and the half are going to cancel. And so I'm going to keep it negative, so I'll have minus integral y e to the 2y dy. So then another integration by parts there. So I'm put y here, and then put e to the 2y dy here. This is going to be dy, this is going to be 1/2 e to the 2y. And so now this becomes, oh my goodness, that's driving me crazy. So this becomes 1/2 y squared e to the 2y minus, okay, we're going to have this times this, so 1/2 y e to the 2y, but then remember this is minus everything we get, so minus 1/2 integral e to the 2y dy. And I can integrate that last piece without any integration by parts. So this will become 1/2 y squared e to the 2y minus 1/2 y e to the 2y, and then plus half, actually I'm going to get another half, so 1/4 e to the 2y plus some constant. Alright, so that is my left side, I'm sorry, my right side. So coming back up here, I have, you know what, I think I wrote something down wrong. No, I didn't. Let me just double check something before I get too far ahead of myself here. Yeah, okay, good. Alright, so now we have e to the y, y squared x equals, okay, 1/2 y squared e to the 2y minus 1/2 y e to the 2y plus a fourth e to the 2y plus c. And I'm going to solve for x, so I'm going to divide everything through by e to the y squared. So x should be, all right, on this first one we'll still have a half. The y squareds cancel, right, when I do that. And e to the 2y divided by e to the y is just e to the y, subtraction of exponents. And then minus, on the second one, when I divide through, I'm going to get an e to the y on top, because I divide. I still have the 2 on the bottom, and I have a y on the bottom, because only one of those factors of y canceled. And then on the last one, or the second to last one, I'm going to have an e to the y on top, and I'm going to have a 4 on the bottom and a y squared. And on my last one, I'll have my constant over e to the y times y squared. All right, how does that look? It looks good. Plus, plus, minus, first one's plus. Okay, yep, we're good to go. All right, so that's number 25. So that's a good example where we had to go with x prime instead of y prime just by looking at it there. All right, let's look at number 26. Okay, you're going to be working number 26. All right, what do we got here? We've got x squared plus x dy. Let me take my watch off. It gets in the way. Okay, x squared plus x dy equals x to the 5th plus 3xy plus 3y dx. Okay, I'm going to go for y prime here because it looks like I've got a function of x sitting in front of dy, and I'll be able to divide that out. So let me divide everything through by dx first. And we should just get these terms on the right-hand side. And now I want to get a function of x on the right side and then anything with a y on the left side. So I'm going to rewrite that. Moving things over. So minus 3xy minus 3y equals x to the 5th. And one more thing here. I need to make this some function of x in front of y, so I'm going to factor a y out. And while I'm at that, I'm going to pull a -3 out of the front. I'll be left with x plus 1 and then a y at the back like that. I think that looks the best. Now, let me divide through by x squared plus x on everything here. All right, let's see what we get. So just y prime here. And then notice that this denominator can be written as x times x plus 1. That's going to make our life really nice because the x plus 1's cancel. So we wind up getting -3 over x times y. Very good. And then on the right-hand side, again, if this is x times x plus 1, one of these x's will cancel out. So we're just going to get x to the 4th over x plus 1. All right, we're ready for an integrating factor. So my integrating factor is going to be e to the integral of -3 over x dx. I'll go ahead and pull the -3 out. Integral 1 over x dx. So we're looking at e to the -3 times natural log of x. Absolute value, but I'm going to go ahead and just make x bigger than 0 here for domain. That way we don't have to worry about it. And that'll be e to the natural log of x to the -3, which is going to just be x to the -3, which again is just 1 over x cubed. And now I'm going to multiply both sides by that. And so I get my derivative on the left side, product rule, which will be my integrating factor times y. Now my right-hand side, when I multiply this by 1 over x cubed, that's real good because I get almost all those x's to cancel. I'm left with x over x plus 1. All right, now I'm going to integrate with respect to x. And let me do that one over here. I have x over x plus 1 dx. And there's different ways I could do this. I'll do it the way that makes probably the most sense. I'm just going to do a basic u sub. I'm going to let the denominator be, let u be x plus 1, d would be dx, and anytime I want to rewrite x, I can solve that for x, I get u minus 1. So this integral now becomes integral x on top is u minus 1, and on the bottom x plus 1 is u, and then dx is du. And now the reason I did that is because I can now split this into two separate terms, u over u, which is 1 minus 1 over u du. And then I can integrate each of those. That's u minus natural log absolute value of u plus a constant. But just remember that u is x plus 1. So I should get here x to negative 3 times y equals u, which is x plus 1, and then minus the natural log of the absolute value of x plus 1, and then plus c. And then I can divide through by x cubed. Equals, so yeah, just remember this right here is 1 over, sorry, I should have said multiply both sides by x cubed. So we should get x to the 4th plus x cubed minus x cubed natural log of x plus 1 plus x cubed times c. All right, let me take a look here. X to the 4. Did I? Well, no, I didn't miss my 3. Okay, gotcha. All right, so yeah, the only thing you could do here is combine those two together. If you do that, you're going to have basically x cubed plus x cubed times c, and you could factor out an x cubed, and you get 1 plus c. But that's just x cubed times a constant plus 1. But the constant is arbitrary, so that's still just x cubed times a constant. So it would be sufficient at this point to just get rid of this x cubed right there, because this actually contains the same information. So that's it right there. It wouldn't be wrong to leave it the way I had it. It's just that's the way the book has the answer. So all right, let's move on. 27. All right, 27x, then it says dy dx, so I'm just going to write y prime plus parentheses 3x plus 1 times y. This looks like it's already in the form we need, e to the negative 3x. Yeah, that looks good. Just divide everything through by x, so we get y prime plus 3x plus 1 over x times y equals e to the negative 3x over x. All right, let's see how this works. We've got integrating factor e to the integral of 3x plus 1 over x dx, which is equal to e to the integral, this is just 3 plus 1 over x dx, splitting it up into two terms, and that's just e to the 3x plus natural log of the absolute value of x, but we'll go ahead and do a domain restriction here, and so we get e to the 3x times e to the natural log of x. We've done that a couple of times now, and then that's just e to the 3x times x, and that's our integrating factor. So the left-hand side becomes the derivative, all right, of the product of our integrating factor, x e to the 3x. Okay, oh, forgot the y, times y, equals, okay, we've got e to the negative 3x over x times e to the 3x times x. So I multiply both sides by the integrating factor, and I think we got some really good things happening here. These x's are gone, and we do these together, add the exponents, we get e to the 0. So the right-hand side is just 1. And this is d dx x e to the 3x times y. Now we integrate both sides with respect to x. So our right-hand side is just going to be x plus a constant, and the left-hand side is just our integrating factor times y. And this will just be y equals, okay, let's divide both sides by x e to the 3x, x e to the 3x. It's gone over here. These x's go away, so I just have an e to the 3x on the bottom. I'm going to write that as e to the negative 3x, and then plus, and I guess I'll just write it as c over x e to the negative 3x, or sorry, to the positive 3x. Let me do it this way as well. Let's erase this. Let's just do it c times e to the negative 3x over x. Okay, let me just check this. That looks good. Okay, all right. Remember, and we're on our domain restriction there. All right, 28. X plus 1 y prime plus x plus 2 y equals 2x e to the negative x. All right, this looks like the form we need. I just need to divide through by x plus 1. So I'm going to have y prime plus x plus 2 over x plus 1 times y equals 2x e to the negative x over x plus 1. Yuck. All right, let's go. Integrating factor, e to the integral of x plus 2, oh, I'm sorry, I said 2 and I wrote 1. X plus 2 over x plus 1 dx. Now, this could be done with the basic u substitution, but I'm going to do this one a little bit, I guess, tricky. I'm going to do something tricky. I'm going to rewrite the top as x plus 1, because that's really x plus 2 over x plus 1 dx. And then I'm going to kind of just split this right here. It's going to be x plus 1 over x plus 1, and then 1 over x plus 1. So we get e to the integral, and when we do that, we get 1 plus 1 over x plus 1. You could also get that using, like, long division. All right, that I can integrate. So that's e to the x plus natural log of x plus 1. And now we need some domain restriction here. We need x plus 1 to be greater than 0, so x needs to be bigger than negative 1. And we drop the absolute value, so we get e to the x times e to the natural log of x plus 1. And these go away, so we just get x plus 1 e to the x. I just flipped the order there. That's our integrating factor. And now we go ahead and multiply both sides by that, and we know that the left side will become that product. So it'll be x plus 1 times e to the x times y. Now we'll equal, now we have to multiply. I have to apologize. I'm always clearing my throat. I don't know what's going on with me. I usually do these videos in the morning. I'm drinking coffee, and for some reason the creamer kind of makes my throat always need to be cleared. All right, so I'm multiplying both sides by x plus 1 e to the x. That's good. These cancel. These become e to the 0, which is 1. So I'm just left with 2x here. Wonderful. Okay, integrate both sides with respect to x. So left side is just this. Right side antiderivative is just x squared plus c. And now I can divide through. So y will be equal to x squared over x plus 1 times e to the x. And then we have plus c over x plus 1 times e to the x. And that should be it. Yeah, they didn't solve that, but that's okay. And remember our domain restriction here, x must be greater than -1. Okay, next one, 29. Feeling like I'm making some progress today. Y dx minus 4 times the quantity x plus y to the 6th. Let me double check that. Term y to the 6th dy equals 0. I think I'm going to go for x prime here. Let's go for x prime because I can kill off this dy over here and it'll free up these x's and y's. So I'm going to divide everything by dy, so we get y times x prime minus 4x minus 4y to the 6th. Distributed that -4 through equals 0. So now what I need is a function of y in front of x prime, which I have. I need a function of y in front of x on the left side, and then some function of y on the right side. So I'm just going to move this 4y to the 6th to the right side, which makes it positive, so I'm just going to cheat here. There. And now I can see I have a function of y in front of x. It's just -4. So that should be nice, because I'm going to have e to the integral of... Oh, sorry, I forgot to divide by y. Oops. Okay, divide by y. Got to get a 1 in front of x prime. So x prime minus 4 over y times x. Divide the right side by y, I get 4y to the 5th. Okay, now integrating factor. E to the integral of -4 over y dy, which is going to be e to the -4 integral 1 over y dy, which is equal to e to the -4 natural log of the absolute value of y. We're going to go ahead and make our y greater than 0 here. And that should turn out to just be e to the natural log of y to the -4, which is just y to the -4. All right, we're going to multiply both sides by that. So we know our left side is going to wind up being a product of a derivative, or a derivative of a product. It's going to be our integrating factor times x this time, and that should equal, okay, so when we multiply the right-hand side by y to the -4, we add the exponents there, we just get 4y. That's real good. Now we integrate both sides with respect to y, and we get, you know what, I wrote dx there, that should be dy. Y to the -4 times x, integrate this with respect to y, we should just get 2y squared plus a constant. And now we solve for x, x will be equal to, okay, we're really multiplying both sides by y to the 4th, so 2y to the 6th plus c times y to the 4th. All right, check this here. And this, of course, is whenever y is greater than 0. All right, 30. So for 30, what have we got? Xy prime plus 2y equals e to the x plus natural log x. All right, I think it's pretty natural to go for y prime here because I've almost got it already. I just need to divide by x. So y prime plus 2 over x, there's my function of x in front of y. And then when I divide the right-hand side by x, I get e to the x plus natural log x all over x. And now I need my integrating factor. So e to the integral of 2 over x dx, yeah, positive. So that's just going to become e to the 2 natural log absolute value of x. Let's go ahead and make x bigger than 0. So this is just going to become x squared. I think we've done enough of those that's pretty clear. All right, multiply both sides by x squared, so we know the left side is going to become the derivative with respect to x of a product or integrating factor in y, and that must equal, multiply the right-hand side by x squared, and this x is gone, we get one factor gone. So I just have to hit each of those with an x. Yeah, oh, I forgot the x. All right, now integrate with respect to x. All right, that's going to be a little bit of work. So let's see, how do I want to do this? I'm going to do them separately, okay? So I'm going to do the integral of x e to the x dx. That's going to be one problem I'm going to do. And I'm going to do integral x natural log x dx. All right, so the first one I'm going to do integration by parts. I'm going to let u be the x and let the dv be this. And then go ahead and just complete the table. And then rewrite this integral using the formula. So this should just be x e to the x minus the integral e to the x dx. Again, I think we've done that enough. And then integrate e to the x is just e to the x. We will have plus c there, but I'll throw it in at the end. Now in this one's a little bit different. I know the temptation is to put x here and natural log x here dx, but the antiderivative up here is ugly for natural log x, so we're actually going to go the other way. We're going to put natural log x here and put x dx here. And then when we differentiate natural log, we get 1 over x dx, and we integrate this, we get 1/2 x squared. And now that'll become 1/2 x squared times natural log x minus 1/2 integral x dx. So when I put those two together right there, one of the x factors cancels and I get a 1/2 out front, so that's why I pulled that 1/2 out. 1/2 x squared natural log x, and now I need to take the antiderivative of x, which is 1/2 x squared, so I get minus 1/4 x squared and then plus a constant. So time to put this all together. The left hand side over here is x squared times y, and then the right side, let me throw that all together. X e to the x minus e to the x plus 1/2 x squared natural log x minus 1/4 x squared plus some constant. And now I need to divide everything by x squared. So we're going to get e to the x over x, that's what happens when I divide that by x squared, minus e to the x over x squared, plus, x squareds cancel here, so I get 1/2 natural log x, and then I get my x squareds cancel, so minus 1/4, and then plus c over x squared. That looks like it. Let me double check it. This was number 30. They didn't divide through by x squared. Okay, that's okay. All right, looks good. And remember, we're on a restricted domain there. 31. Got a little groove. I'm in a groove right now. Okay, dy dx, so y prime plus y equals, 1 minus e to the negative 2x over e to the x plus e to the negative x. Wow, that is really ugly. But this is the form we need. This is it, so there's nothing I need to do other than get an integrating factor. So I need to do e to the integral, and I have a 1 in front of the y, so I'm just integrating 1 dx. And that's just going to be e to the x. That's my integrating factor. So I will multiply both sides by this. So I know my left side's the derivative with respect to x of, yuck. Okay, e to the x. Sorry, I said yuck because the emails that are popping into my inbox right now. Okay, equals. All right, so how do I want to multiply this? Let's do this, times e to the x. Let's go ahead and multiply through the top. So we're going to distribute here and here. Let's see what we get. We get e to the x minus, now we add the exponents, negative 2x plus x is just negative x, so e to the negative x over e to the x plus e to the negative x. Now, I'm curious now if we're wanting to bring in hyperbolics, but because those look like hyperbolics, but I don't believe, let me look at what the book does. The book doesn't mess with hyperbolic, so I'm not going to either. All right, so there's where we are. Integrate that with respect to x, integrate that with respect to x. We get to do that on the side. Gosh, tempted to do something. Let's do, I want to do long division. That's what I really want to do. Let's try something first. We have e to the x. I'm just going to look at this algebraically first. Maybe we can clean this up. Do something. E to the x plus e to the negative x. Let's multiply the top and bottom by e to the x. Let's just see what happens. We get e to the 2x minus 1 over e to the 2x plus 1. I still don't like this. Still don't like that. Hyperbolic would be much easier to do here. Can I do that? I don't want to go through this, but maybe I will. All right, let me use long division. I mean, that was my initial instinct, but okay, let's go e to the x minus e to the negative x, and then let's put e to the x plus e to the negative x here, and then let's go ahead and multiply. So to make this turn into this, we need a 1. So we multiply by 1. That'll give us e to the x plus e to the negative x, and then from there we subtract. So this is going to change the signs. It becomes minus, and then minus. And we add down there, these go away, and we get negative 2e to the negative x. And now, I think what I'll do here is I will I think this is just going to be my remainder, minus 2e to the negative x over e to the x plus e to the negative x. God, I really don't like that. Okay, so what would happen if I try and integrate that? Integrate 1 minus 2e to the negative x over e to the x plus e to the negative x. The first one's easy, that's just x, but then we have to do this integral. That integral, I would make it maybe a basic u sub. U is equal to e to the x plus e to the negative x. The derivative of that would be, oh shoot, I can't believe I didn't see that right away. Ah, bless. Okay, well, that's why I'm doing this, so you can learn from my mistakes. It's nice to work through these problems. Well, I'm trying to work through these problems without going through them first. And should have just done this to begin with. So look, let's just make a basic u substitution. And nothing to be ashamed of. Okay, here we go. So watch, when we take derivative of this, we get e to the x, but then because of that negative up there in chain rule, the derivative of e to the negative x is negative e to the negative x dx, and that's exactly what we have on top. And that's just crazy. Okay, that's too easy now. So integrating that with respect to x, making that substitution, we just get, rewrite the integral. This right here is du, and the bottom is u. So this is 1 over u du, which is just natural log of the absolute value u, plus constant. And u is that. Wow, that's so simple. Okay, so e to the x times y equals natural log of e to the x plus e to the negative x plus a constant, and then I divide through by e to the x. So I'm going to rewrite that as dividing through by e to the x is the same as that. And plus c times e to the negative x. All right, that should be y. Let's check. Yeah. Okay. And we never had any restrictions on x on this one, so all real numbers. Well, that was interesting. Everything was flowing pretty good until that one. Let's go to number 32. I'm imagining I'm going to run into more issues here as we move along. Okay, y prime minus y equals sine hyperbolic x. Hey, there we go. So this one has a hyperbolic in it, so maybe I should remind you of what sine hyperbolic really is. Sine hyperbolic x is really 1/2 e to the x minus e to the negative x. And cosine hyperbolic is 1/2 e to the x plus e to the negative x. So, yeah, great. Let's go. Let's do this. We've got everything we want. 1 in front of this. We've got a number in front of y, or a function of x. So my integrating factor, I may not need this. I just wanted to throw it out there. -1 dx. So this is just e to the negative x. So I multiply both sides by that. When I do that, my left-hand side becomes that product, the derivative of the product, e to the negative x times y, and then equals, now I've got to multiply this by e to the negative x. So that's why I'm thinking that it might be worth it to rewrite hyperbolic sine as 1/2 e to the x minus e to the negative x, and then I'm going to multiply that by e to the negative x. Yeah. So let's distribute that through. We're going to have 1/2. Okay, when I multiply here to here, we just get e to the 0, which is 1. And then here to here, we get minus e to the negative 2x, like that. Yeah, good. And let me go ahead and just put that 1/2 through. 1/2 minus 1/2 e to the negative 2x. And that's, I'm going to integrate this side with respect to x, and then integrate the left side, and we know the left side's just this. Okay, we're moving now. The antiderivative of this I should be able to do without anything. So antiderivative of 1/2 is 1/2 x. And here we got a little chain rule here. If I just kind of ignore this, the antiderivative of e to the negative 2x would be negative 1/2 e to the 2x. So I'm going to hit that with the negative 1/2 that's already there, so it's going to become plus 1/4 e to the negative 2x, and then plus some constant. And that's my left side. So now I'm really going to just like multiply both sides by e to the x. That's really what's going to go on here. If I do that, I get 1/2 x e to the x, and then plus 1/4. And when I multiply this thing by e to the x, I just wind up with e to the negative x, and then plus c times e to the x. All right, which one was this one? Number 32? Yeah, we're good. All right. All right, gonna be working here now. 33. Okay, y dx plus x plus 2xy squared minus 2y dy equals 0. So I'm going for x prime here. So I'm going to divide everything through by dy. So y x prime plus x plus 2xy squared minus 2y equals 0. Now what I need to do is have a function of y in front of x, and then a function of y on the right hand side. So I'll move this negative 2y to the other side, that'll make it positive 2y. Let me factor out the x here of the second two terms on the left side. So we're left with 1 plus 2y squared x. And then let me divide through by y. And that should be it, dividing everything by y. So now my integrating factor, oh, let me pause, hold on. Okay, integrating factor, so e to the integral of 1 plus 2y squared over y dy. That's going to be e to the integral of 1 over y plus 2y dy, just breaking that up into 2, which is e to the natural log of y. We're going to go ahead and get our domain y bigger than 0. And then the antiderivative of 2y is y squared, so we're going to have times e to the y squared. E to the y squared. And then this just becomes y. And then this right here becomes e to the y squared. Okay, let's see here. Yeah. All right, so there's our integrating factor. This should turn into the derivative with respect to y of our integrating factor times x. And I need to multiply the right-hand side by the integrating factor, so 2y e to the y squared. And now I'm going to integrate with respect to y on both sides. And fortunately for us, this integral is straightforward because the y squared up in the exponent, we can just do a basic u sub. U is y squared. Derivative of that is 2y dy. We have 2y dy. So this is just e to the u du. And the antiderivative of that is just e to the u plus c. But u is y squared. So my right-hand side should just be e to the y squared plus some constant. And then my left side is y e to the y squared times x. And now just divide everything through by y e to the y squared. So we get x is equal to, let's see, we should just get 1 over y, and then plus c over y e to the y squared. And that should be it for 33. Yep, okay, good. All right, 34. I feel like I'm making some progress here. Y dx equals y e to the y minus 2x dy. Alright, again I'm going to go for x prime here. We're going to get y, so dividing through by dy, x prime equals, everything here can be taken out of parentheses because I divided through by dy. And now what I need is a function of y on the right hand side, which will be this, and then some function of x on the left, so y times x prime plus 2x equals y e to the y. Divide through by y. Now I have a function of y in front of x, and equals e to the y. And now I will get my integrating factor. And I'm doing 2 over y dy. I think we've done this so many times. Let's see, e to integral 1 over y dy. Restrict us, y bigger than 0. It's going to be e to the natural log of y squared, which is just y squared. So, we have the left side is the derivative with respect to y of y squared times x. Then equals y squared e to the y, multiplying the right side by the integrating factor. Now I need to integrate that, and that looks like integration by parts this time. Looks like we're going to have to do it twice. So y squared here, e to the y here. This is 2y dy. Sorry, that was dy there. and e to the y. So this becomes y squared e to the y minus 2 times the integral of y e to the y dy. And now I do integration by parts again on this piece right here. So we have this time y here, dy here, e to the y dy, and e to the y. So we get y squared e to the y minus 2. Now here comes my integration by parts on the second one. Y e to the y minus integral of e to the y dy. And I can get a final answer here. Y squared e to the y minus 2y e to the y, and then plus 2e to the y, and then plus a constant. So antiderivative, that's just e to the y. I'd have to distribute that negative 2 through, so we should be there. Y squared x equals the antiderivative, right, both with respect to y here, which is y squared e to the y minus 2y e to the y plus 2e to the y plus c, and then I divide through by y squared. I'll let you do that yourself. Just check it. And then 2 over that. Wait a minute. Okay. Let me just do it. Okay, so x is equal to e to the y minus 2 over y e to the y when I divide through by y squared, plus 2e to the y over y squared, plus c over y squared. Okay, c over y squared. Where's my c over y squared? 2 over y squared. Where's just 2 over y squared? I don't think this is right. What am I missing? This is not matching up with the answer. Am I looking at the wrong one? E to the y minus 2. I'll pause it real quick, double check something. All right, I'm going to stick with that. Move on. Basic ideas done. 35. All right. Ooh, got some different variables here. I'm going to write the way it's presented. dr d theta plus r secant theta equals cosine theta. All right. So really this is kind of like r prime plus some function of theta in front of r, and then equals some function of theta. So that looks exactly like what I would need to get an integrating factor. This time secant theta is going to be what I use here. Secant theta d theta. I didn't have to divide through by anything because I had r prime by itself. So we need to get the antiderivative of secant theta, which is in our formulas, and it is natural log of secant theta plus tangent theta. So this is going to be natural log of secant theta plus tangent theta, and then that should be able to be rewritten as e to the natural log of 1 over cosine theta plus sine theta over cosine theta. I'm going to write it like that. And then now I can go e to the natural log of 1 plus sine theta over cosine theta. So long as this is positive inside here, then we should be in business. And the only time The numerator should always be positive because it's 1 plus sine theta. I mean, sorry. Yeah, we could have negative 1 there. We could get a 0 on top. That would be a problem. So we don't want sine to ever be negative 1. That would be at negative pi over 2. But then we also want this to be positive, and cosine of theta. So we got to restrict ourselves theta here between pi over 2 and negative pi over 2. Negative pi over 2. Let's see why that's true here. So as long as we're here, cosine is positive, right? The x-coordinate. So, and then we can't be at here. We can't be here because then sine will be negative 1. We'll have 0 on top, so that's a problem. Also can't have cosine be 0. So that's our restriction. But this now allows us to use property of logs to rewrite that as e to natural log of 1 plus sine theta minus natural log of cosine theta, like that. And now I can rewrite that as e to the natural log of 1 plus sine theta over e to the natural log of cosine theta. Oh man, why did I should have just killed these off in the beginning. It doesn't matter. I'm working too hard. So at the end of the day, this is just 1 plus sine theta over cosine theta. All right, that's our integrating factor. It's strange, but it is what it is. In fact, I could rewrite that as just back at secant theta plus tangent theta. I'm not sure. I think I like it this way. So I know my left side becomes the derivative with respect to theta, okay, of 1 plus sine theta over cosine theta times r. And that equals the right-hand side times the integrating factor. And that's nice because these cosines cancel. So we just get 1 plus sine theta. We're now going to integrate with respect to theta. And that should give us a really nice answer here. Antiderivative 1 with respect to theta is just theta. And then minus cosine theta plus some constant. And yeah, left-hand side is just our integrating factor times r. And now we can solve for r. Now, wonder what the book does. Do they solve for r? They did not, and I will not. So this is it. I'll just leave it like this. All right. Moving along. 36. So for 36, we have dp dt plus 2t times p equals p plus 4t minus 2. Let me just double check that. dp dt plus 2t p equals p plus 4t minus 2. All right, so now I'm going to be going for p prime here. All right. Which means the next one needs to be a function of t in front of p, which I have, and the other side needs to be a function of t only, which it's not. I have that p here, so I need to bring that p over to the left side. So minus p equals 4t minus 2. That throws a little bit of a wrench into things because I've got to factor that p out. So 2t minus 1 times p, and now that's my function of t in front, equals some other function of t. So now my integrating factor, 2t plus 1, nice, dt. So that's just going to be t squared e to the t squared minus t. Oh yeah, that's real nice. Okay, so now we know my left side becomes the derivative with respect to t of the product of the integrating factor and p, and that must equal 4t minus 2 times the integrating factor. And now I need to integrate that with respect to t. And we'll notice that this piece right here if we call that u, the derivative of that is just going to be 2t minus 1 dt. And we almost have that right here. We have 4t minus 2. So if I multiply both sides by 2, we have it. So that integral is really just 2e to the u du. And now we integrate. So the antiderivative would just be 2e to the u. So this would be 2e to the u, but u was t squared minus t, and then plus some constant. That must equal e to the t squared minus t times p. And now we can divide through by this thing. I'll do that because it's not too bad. So I divide the first one, I get 2, and then plus c over that. Like that. Alright, which one was this? Yeah, okay, that's good. It's 36, so 37. X plus 2 squared times y prime equals 5 minus 8y minus 4xy. Alright, I'm going for y prime here. So x plus 2 quantity squared times y prime plus 8y plus 4xy equals 5. So I got the things with y on the left. I've got to factor a y out of this, so I'm going to just rewrite it. So that's going to be 8 plus 4x, and then there's the y I pulled out. And now I divide through by x plus 2 squared. So y prime plus 8. I'm going to rewrite that as 4 times 2 plus x, and the reason I did that is because I'm about to divide through by x plus 2 squared, and I kind of saw that it was going to cancel. At least one factor will reduce out. Then 5 over x plus 2 quantity squared. So see here, boom, boom, that's nice. Okay, so we're doing e to the integral of 4 over x plus 2 dx, like that. This is e to the 4 times natural log of x plus 2. That's valid as long as x is bigger than negative 2. And so the 4 is going to come up, and so we're just going to get the e natural log to cancel, so we're just going to get x plus 2 to the 4th. That's our integrating factor. So our left side becomes the derivative with respect to x of x plus 2 to the 4th times y, and then equals, I multiply this by x plus 2 to the 4th, so we get 5 times x plus 2, that quantity squared. And now we are ready to integrate with respect to x. So left side becomes x plus 2 to the 4th times y. This one, with respect to x, you can just do a basic u sub. U is x plus 2. And so we should get, I'm going to trust you can get that 5/3 times x plus 2 cubed, and then plus some constant. We divide through by x plus 2 to the 4th. So we get 5 over 3 times x plus 2, because 3 of the factors canceled, then plus c over x plus 2 to the 4th, like that. Okay, that was 37, and that looks good. All right. 38. X squared minus 1 y prime plus 2y equals x plus 1 squared. Alright, going for y prime here. Everything looks good. Just divide through by x squared minus 1. that y equals x plus 1 squared over x squared minus 1. Eey. All right, that integrating factor looks like it's going to be a little messy. We have e to the integral, and let me bring the 2 out, of 1 over x squared minus 1 dx. All right, so I'm thinking that what we're going to need to do here is partial fractions. Partial fractions. Yeah, let's work this. We're trying to integrate 1 over x squared minus 1, which is x plus 1 is x minus 1, like that. And then we know from partial fractions we can try and rewrite this as some constant over x plus 1 plus some constant over x minus 1, which means that if we multiply both sides by the denominator x plus 1 times x minus 1, we should get 1 equals a times x minus 1 plus b times x plus 1. And now we solve for a and b. So I'm going to let x be negative 1. That'll kill off the b. And if I do that, we get the equation 1 equals negative 2a. So a is negative a half. And then we can do the same thing to get b by letting x be 1. If we do that, we get the equation 1 equals 2b. So b is positive a half. So this integral up here becomes a, which was negative 1/2, over x plus 1, and then plus b, which is positive 1/2 over x minus 1. So we're trying to integrate that. All right, that should be pretty straightforward. I'm going to continue that over here. We have negative 1/2 integral of 1 over x plus 1 dx, and then we have plus 1/2 integral of 1 over x minus 1 dx, and those are just natural logs. So 1/2 natural log of x plus 1, and then plus 1/2 natural log of x minus 1. All right, so remember that's all my integrating factor, right? I've got to figure it out. So I had a 2 in front of all that, so the 2 is going to come through and make this go away, and make that go away when I hit that with the 2. And that's going to be e raised to that. I know I'm kind of all over the place here. So that's where I am. And then I have subtraction between logs. I have this log minus this log. So that becomes e to a single log with division inside, x minus 1 over x plus 1. And now at this point, the e and the natural log cancel, so all you're left with is this. Okay, now I'm not going to get too much into the domain here. I'll just kind of leave it to you to show that x must be between 1 and negative 1 in order for this ratio here to be positive so that the natural log makes sense. So I think we can just proceed at this point. So what I'm going to do is, oops, no, not that. Remember our integrating factor is, where did I put it? Oh, it's this right here, x minus 1 times x plus 1. X minus 1 times x plus 1. Okay, so coming back up here, and let me do the right side first before I forget. X plus 1 squared, x squared minus 1, times my integrating factor, and yes, I did forget it already, x minus 1 over x plus 1. Now on the left side, we know it's going to turn into the derivative with respect to x of the integrating factor, x minus 1 over x plus 1 times y. And now we integrate both sides with respect to x, but we also get some things to turn out nice here, like this x plus 1 cancels with one of those. Remember, this is really x plus 1 times x minus 1. So the x minus 1's cancel, and another factor of x plus 1's cancels. So all we have here is a big old fat 1. So the antiderivative of that's just x plus a constant. and that equals x minus 1 over x plus 1 times y. And then we can multiply both sides by the reciprocal of this, which gives us x times x plus 1 over x minus 1 plus c times x plus 1 over x minus 1. All right, let me double check that because that was quite a bit going on there. Okay, that looks good. So right here. All right, 39. Getting a little bit tired of doing this. 39. Oh, this one looks pretty straightforward. Alright. So what I'm going to do first is distribute the cosine hyperbolic x through. Okay, I need my y guy over here on the left-hand side, so y prime plus, now I'm going to write it backwards because I need a function of x in front of y, and then the right-hand side, 10 cosine hyperbolic x can stay, and I'm ready. Integrating factor, e to the integral cosine hyperbolic x dx, and that's a nice one because the antiderivative cosine hyperbolic x is sine hyperbolic x. So this is equal to e to the sine hyperbolic x, and that's my integrating factor. So I know that my left side is the derivative with respect to x of e to the sine hyperbolic x times y, and then if I multiply the right-hand side by e to the sine hyperbolic x, I get 10 cosine hyperbolic x times e to the sine hyperbolic x. And that's going to be easy to integrate. Integrate left, integrate right, respect to x. Left side's e to the sine hyperbolic x times y equals, over here, this is basic u sub. There's your u. The derivative of that is right there. You got a 10 there, I can just pull that out. So it's really like e to the u du. So the antiderivative is just e to the u, which is e to the sine hyperbolic x plus some constant, and then I divide through by sine hyperbolic x. So it's gone there, and here it appears sine hyperbolic x there. So y is equal to 10 plus cosine c over sine hyperbolic x, which is really cosecant hyperbolic x. Let's see what we got here. Wait a minute. What happened? Oh, e to the, sorry, I'm wrong. Boom, like that. E to the sine hyperbolic x. So it is not cosine hyperbolic x, sorry. I'm getting a little bit tired. It's time for lunch. All right. Number 40 is going to be the last one I do for now. 40. Okay, dx equals 3e to the y minus 2x dy. All right. Should we go for x prime? Let's go for x prime. See what happens. X prime, multiplying, dividing both sides by dy. And now I need something with x in front, so, or something in front of x, so x prime plus 2x equals 3e to the y. That should work. I have function of y on the right. Got some function of y in front of x. Integrating factor, integral 2 dy, sorry, 2 dy. That's just going to be e to the 2y. That's our integrating factor. So we know the left is derivative with respect to y of e to the 2y times x. And then the right-hand side is this times e to the 2y, which is 3e to the 3y. And then I integrate that with respect to y on both sides. Nice. Left side, e to the 2y times x equals, here the answer is just e to the 3y plus a constant. And now divide by e to the 2y, so x equals e to the y, subtracting 3y minus 2y, plus c e to the negative 2y. I just brought it up. Let's see if that matches what they've got here. Looking good. Okay, break time for me. Okay, we're working number 41. Now things are going to change here a little bit, because now what we're asked to do is solve the differential equation, and then after we solve it, we need to use the initial condition to get the exact function in question that solves the equation. So it's an initial condition problem here. So we're going to solve it just the way we did before. I don't know if I'm going to solve all of these. I might just share what the solution is, because I've gone through 40 of these already. But let's at least work this first one out. We have the following differential equation with the following initial condition, that y of 0 is equal to 2. All right, so solving this, it's in the form we want already. My integrating factor is going to be e to the integral of 5 dx, which is just e to the 5th power. 5x. And now I'm going to just rewrite this. This is the derivative of the product of e to the 5x times y equals 20 e to the 5x. All right, so now we integrate with respect to x. The left side is just e to the 5x times y, and that equals, now this one will come out to be 4e to the 5x plus a constant. And now we divide through by e to the 5x, and we get 4 plus c times e to the negative 5x. All right, so that's what we had done in the previous 40 problems. But now what we want to do is we want to use this initial condition. So we know that this function contains a constant, and we want to determine what that constant is in order to satisfy that y of 0 equals 2. So we're really looking at this y here as being a function of x. So what we want is, when we plug 0 in, that spits out 2. So when we replace x with 0, we should get 2 out. So when we do that, this is just going to be e to the 0, which is 1, so we just get 4 plus c equals 2, so c must be negative 2 in order for this to be true. And we could rewrite the final answer like this: 4 minus 2 e to the negative 5x. So this is the specific function that satisfies this differential equation up here, but also you could almost say passes through this point if you were to graph it. Okay, that's 41. Let's take a look at 42. So we have y prime equals 2y plus x times e to the 3x minus e to the 2x, and our initial condition is again y of 0 equals 2. Alright, so this is of the form, let me put it in the form first so that kind of gets you to where you would need to go. Let's see, the right hand side, let's keep it as x e to the 3x minus e to the 2x. So the left side, we've got 1 in front of y prime, we've got some function of x, negative 2, in front of y, and then the right side is some function of x. So our integrating factor here would be, I guess I'll do this one the whole way, e to the integral of negative 2 dx, which is e to the negative 2x, just like that. So now the left side becomes the derivative with respect to x of our integrating factor times y, and then equals, now I'm going to multiply this side by e to the negative 2x and distribute that through. And when we do that, we're going to get x, and then we're going to get e to the x, 3x minus 2x is x, and then we're going to get minus e to the 0, which is 1. And that now gets integrated with respect to x. So left side is e to the negative 2x times y, and then equals, okay, this integral will become integral e to the x minus x. We go ahead and integrate that. We're going to need integration by parts, and I think you could probably do that the rest of the way. So I'm just going to write out what this, when we solve for y, what it would be. So trusting you can do that integral, y equals x e to the 3x minus e to the 3x minus 1/2 x squared e to the 2x plus c e to the 2x. And when you do that, now what you do is, again, we're looking at this y as really being a function of x. When we plug 0 into this, we need to get 2. So y of 0 needs to be 2, but that means that, let's see, when we plug 0 into this, we get, you know, this goes away, that's 0. And then we get minus e to the 0, which is 1. And then when we plug 0 in here, it's gone. And then when we plug 0 in there, we get plus c e to the 0 is 1. And that must equal 2. So you get c must be 3. Right. Yep, okay. I'm not going to rewrite the whole, I'm not going to redo that with c plugged in, you know, right there, 3, done, but not going to do that. Okay, let's see, number 43. So we have L, this is a weird one, L di dt plus r times I equals E, and they're telling us that L, R, and E are constants, and they're giving us that I of 0 equals I sub 0. Okay. What? All right, so let's see. We're going to be looking at this as like this is our y prime. That's like dy dx. That means we need some function let me see, so we need some function of t in front of I, which would be this r is a constant. And then over here we need some function of t, which is just e, which is a constant. So this is going to work. We need to divide through by L first. So di dt plus r over L, maybe I should have done that first, times I equals e over L. Okay, so my integrating factor is going to be e to the integral of r over L, because that's what's in front of the I, dt here, and so that's just a constant up there, so this is going to be e to the r over L times t. That's our integrating factor. So left-hand side is the derivative of the product of our integrating factor, r over lt times I. And then we have equals, now we need to multiply this here by e to the r over lt. So e over L, e to the r over lt. And now we're going to integrate this with respect to t. All right, so now the left-hand side is just e to the r over lt times I equals, okay, e over L is a constant, and then times, let's see, the antiderivative of this with respect to t, remember r over L is a constant, so we just do a basic u sub. You should get L over r times e to the r over lt. You can check that for yourself, plus a constant. And these L's are gone. So we get, let me just replace that. This is going to be e over r, capital E over r. And now I divide through by this. So we get I, which winds up being a function of t, is equal to, so we divided through by this, so we're just going to get e over r here plus c over e to the r over lt. All right, that's it right there. We need to figure out what c is, but we're told that when we plug in 0, we should get I sub 0. So when we plug in 0 into this, it should spit out I sub 0, which means that when we do e over r plus c over, now I'm replacing this t with 0, which makes the bottom there 1, we should get I sub 0. And so that means c must be I sub 0, I'm just solving for c here, minus e over capital R. All right, let me double check this. 43. Yes. Yep. Okay, so if we wanted to rewrite this, you know, we could rewrite the final answer as being this and replace that C with that right there. Okay. Next one, 44. Okay, y dx dy, so I'm going to put y prime minus x equals 2y squared, and we're given that y of 1 is 5. Okay, I think you could handle this one because this one is, we're going to do it for x prime, so we've got a function of y in front. We've got a function of y in front here, which is 1, and then over here we have a function of y. You know what, I should take that back. We should divide through by y. Oops. Let me get it to that stage at least. Divide everything by y. Okay, so now we have 1 in front here. We've got some function of y here, some function of y here. So I would trust that you could go through the rest of that, and you should, at the end of this, dot, 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 get x equals 2y squared plus c times y. And then there are some domain restrictions on this. Y has to be bigger than 0. So now we just use this information that, oh, we have to be a little careful here, because this is telling us what x is, and this is the output, right? So this is like the y. So what that means is when we try and solve this for c, we actually want to say 1 must be equal to, sorry, x, yeah, 1 must be equal to 2 times 5 squared plus c times 5. So we've got 25, that's 50 here, 50, subtract 50 on both sides, get negative 49 equals 5c. So that means that c is negative 49 over 5. So that's what we should get for that. And then we could, again, take it and plug it back in right here, and we'd have a kind of our solution. Okay, 45. Okay, y prime plus tangent xy, this is the way they have it written, equals cosine squared x. They're telling us that y of 0 is negative 1. Okay, I think you could probably handle that because we have done, you know, enough of these. So let me take you to what you get for y. You get y is equal to sine x cosine x plus c times cosine x. And there's some domain restrictions here, but we're not going to worry about those. Let's solve this for c. So just replace all your x's with 0 and y with negative 1. So negative 1 must be, let's see, sine of 0 is 0, so it's going to kill this whole thing off. And then cosine of 0 is 1. So all you get is c is negative 1. And that's it. Okay. Let's look at number 46. Okay, you have dq dx equals 5x to the 4th q. And they tell you that q of 0 is negative 7. So it's like I'm going to be doing like q prime here if you want. And then I'm going to bring this minus 5x to the 4th q to the left and equals 0. So there's your little function of x in front of q. Here's your other function of x. Got q prime with a 1 in front. So my integrating factor, you know, you go work that. That should be pretty clean. Again, I'll let you work that yourself. And so at the end, you just get this. You get q is equal to some constant times e to the x to the 5th. All right, and now we just plug in 0 for x and -7 for q. So -7 must equal c times, and then that's just going to turn into a 1 when you plug in 0 for x. So you get c is -7. All right. Okay, now 47. I'm getting excited. I'm getting close to being done with this section. 47, we get dt, or we have dt, d capital T, d little t, equals k, which is some constant, times capital T minus 50. And they tell you that t of 0 is 200. So capital T is a function of little t here. So we got to make this looks like we're going to have like a t prime, and then minus k times t, and then equals -50k. So just distributed this through, and then moved the k times t over to the left, and then left the -50k on the right. So we have a 1 in front of t prime. We've got some function of little t in front of capital T, and then over here we have some function of little t, which is a constant. So what we would be doing here is we'd be doing e to the integral of -k, which is e to the -kt. That's what our integrating factor would be. So I'll let you again finish that up. You get at the end of this t equals 50 plus c times e to the kt, and now we're going to just solve for c. So replace t with 200 equals 50 plus, and we're replacing t with 0, so that's just going to give you c. So 150 is c. It's easy if you've got the differential equation solved, and it's just really just plugging things in. Man, you know what? I really don't know if I want to work through the rest of those. Let me just give you the answers, because I think it's really, there's nothing more here. 48, you should get c is equal to -1. So for 49, you should get c is equal to 21. And for 50, let's see, c should be 2 minus e. 51, you should get c is 2. 52, c is -1. 2 more. 53, c is 8. And 54, lastly, c is -4. All right. Hopefully you can work through the problems and get to those c's. That'll be good for right now. Okay, we're going to be working number 55, and things are a little different here for these last 4 problems. So what we're given is that y prime plus 2y equals some function of x. And then we're told that the function of x is a piecewise function. And in this particular example, it's 1 whenever x is between 0 and 3, including both 0 and 3. And it's 0 if x is bigger than 3. So what we're supposed to do is find a continuous function satisfying each differential equation and the given initial condition. So we also want that y of 0 equals 0. Okay, so let's take a look at what's happening on the interval 0 to 3. So on that interval, the function f of x is equal to 1, so our differential equation becomes just this. And that, we've done this over and over, so should be comfortable seeing that this is just e to the 2x for our integrating factor. And now we know that the left side is the derivative with respect to x of our integrating factor times y. And that equals 1 times the integrating factor, so just e to the 2x. And then we go ahead and integrate both sides, so we get e to the 2x times y equals, we're integrating both sides, so we get 1/2 e to the 2x plus some constant called c1. And let's see, we know that if we divide through, we get y, which is some function of x, is equal to 1/2 plus c1 times e to the negative 2x. So just dividing both sides there by e to the 2x. But we also have the initial condition that y of 0 has to be 0, and since we are looking in this interval, right, where x is between 0 and 3, we can actually solve for what c1 would be. So we know the left side must be 0 whenever we plug in 0 for x. So we get this plus 0 into here, that would give you just c1. So that tells us that c1 is equal to negative 1/2. So here's what we've got. We've got that on this interval, our function of x is going to be 1/2 minus 1/2 e to the negative 2x. Okay, that's on the interval 0 to 3. Now what we do is we're going to kind of start the problem over again, and we're going to say that if we're looking on the interval where x is bigger than 3, then our differential equation becomes y prime plus, what the heck is that? Okay, never mind. Plus 2y equals, well now we're on bigger, where x is bigger than 3, so if we go back to up here to our piecewise function, our function must be 0. So this must be 0, and we already know our integrating factor is e to the 2x, so we know the left side, so nothing changes here. Left side is going to be e to the 2x times y, but this time when we multiply the right side by the integrating factor, we just get 0, and that means e to the 2x times y must equal, when we take the antiderivative of both sides, some other constant, c sub 2. So dividing through by e to the 2x, we get c sub 2 e to the negative 2x. Okay, so here's what we've got. I'll just say y is some function of x. The thing is, we cannot plug 0 into this because we're not looking on the interval that has 0 in it. We're only looking where x is bigger than 3. So what we have right now is a function. We're trying to come up with an overall function, which we can call y. Let's just say y. Right now what we know is this. On the interval 0 to 3, we know it's, where is that thing? It's 1/2 minus 1/2 e to the negative 2x. And on the interval where x is bigger than 3, we know it's c sub 2 e to the negative 2x. So what we want is to try and figure out what would make this function continuous, all right, a continuous solution. So our discontinuity is happening here at 3, right, when we have a switch over from 3. So what we want is basically that the limit as x approaches 3 of this function, so that means if we're approaching 3, let's approach it from the right hand side, that means we'd be looking here. We want this limit as x approaches 3 to be equal to the function's value at 3, and so if we're at 3, we're going to be right here, so that needs to be equal to 1/2 minus 1/2 e to the negative 2 times 3. Okay, so now we can just take this limit, let x go to 3, so we get c sub 2 e to the negative 6 must equal 1/2 minus 1/2 e to the negative 6. I'll divide through by e to the negative 6, so you get 1/2. When you divide by e to the negative 6, it's the same as multiplying by e to the 6th, and you get that, and then minus 1/2. That should be our c sub 2. So now what we do is, I'm just looking at something, yeah. So now what we do is we come back up here and we replace our c2 with that. So I'm going to do that. I'm just going to save some space here. So in front of that, our c sub 2 we know needs to be 1/2 e to the 6th minus 1/2. So that equation right there, that function of x, it's a piecewise function, will satisfy the original differential equation, which is here, where this function is this piecewise function. So that's it. We are done with that one. Let's look at 56. Just going to follow the same sort of method here. So for 56, we've got y prime plus y equals some function of x. Here we're told that this function of x is again piecewise. It's 1 and negative 1. It's 1 if x is between 0 and 1. Make sure I get this right. And it is, when it's bigger than 1, it's negative 1. And we're given that y of 0 equals 1. Okay. I should have mentioned on the previous problem that this function that we found not only satisfies the original differential equation, where f of x is this piecewise, but it also satisfies this initial condition. Okay, so we also had that in there. I forgot to say that. So let's go ahead and go through this again. This is a perfect form that we need. Let's look on the interval between 0 and 1. And I like to use that one first because we know the initial condition is in there, so we should be able to solve for the constant. If we do that, then our differential equation looks like this. We're working in the top piece, so this right side is 1. And now our integrating factor, I'll let you get that yourself. The integrating factor should just be e to the x. So we get that d dx is e to the x times y, and that must equal the right-hand side times the integrating factor. And now we just integrate, so we get e to the x times y equals e to the x plus a constant, I'll call it c1. And we divide through by e to the x, we just get 1 plus c sub 1 times e to the negative x. And now we know that we were told that y of 0 equals 1. So y of 0 equals 1 means that this equation up here becomes 0 equals, equals 1. So 1 equals 1 plus, and again, plugging 0 into this, we should just get c sub 1. So that means, is that right? 1, so we should get 0. C sub 1 is 0, is that right? D6. Yes, well, hold on. Yeah, okay. C sub 1 equals 0. That's kind of strange because that means that y is equal to just, if c sub 0 is 0, then that means y is 1. Okay, all right, let's keep going. Now, on the interval where x is, what was it, bigger than 1, our differential equation becomes y prime plus y equals, now it's negative 1 because we are looking here instead. And when we do that and go through the same story, we get d dx of e to the x times y equals negative e to the x, and then we integrate both sides, we get e to the x times y equals negative e to the x, so the antiderivative of that's just that, and then plus some other constant, and so that means that y is equal to negative 1 plus c sub 2 times e to the x, negative x. Alright, so now here's what we know about y. Y is equal to the constant 1 function if x is between 0 and 1. And if x is bigger than 1, it's equal to negative 1 plus c sub 2 e to the negative x. And now we need this to be continuous, and we're really only looking at 1 because that's where it switches. So we need the limit as x approaches 1 from the right, because that would put us here, of negative 1 plus c sub 2 e to the negative x. We need that to be equal to what it is at 1, which is 1. And now when we take this limit and let x approach 1, we get negative 1 plus c sub 2 e to the 1 must equal 1. And now I'm going to solve for c sub 2. So c sub 2 e must equal 2. So c sub 2 must equal 2 over e. So I just added 1 to both sides and divided by e. And yeah, okay, so now we know what this c sub 2 is, so I'm just going to come back up it here and replace it. So we should have here 2 over e. Alright, I'm going to just double check that. Okay, I see a little bit of a mistake here. When I plugged 1 into this limit right here, oops, when I plugged 1 into that right there, it should have been negative 1 right there. And that's negative 1, and so this next line should be 2e. There we go. So this should be 2e times that, and you could rewrite that as e to the 1 times e to the negative x is just e to the 1 minus x. Yeah, that would be okay like that. Okay, so there we go. That's it. It satisfies the differential equation, and it also satisfies the initial condition, where the right side of this is this piecewise function. Alrighty, let's look at 57. Okay, y prime plus 2xy. Let me make sure I'm recording. I don't remember if I hit that button. Yeah. Okay, 2xy equals some function of x, where that function of x is x if x is between 0 and 1, and it's equal to 0 if x is bigger than 1. Oh wait, oops, I messed that up. That's less than 1, and this one is greater than or equal to 1. And our initial condition is y of 0 equals 2. Alright, so let's take a look at this. This differential equation is in the perfect form, so on the interval 0 to 1, when we do that, we get y prime plus 2xy equals x. And our integrating factor is e to the integral of 2x, which is just e to the x squared. So this left side becomes a derivative with respect to x of e to the x squared times y equals x e to the x squared, multiplying both sides by the integrating factor. And now we integrate with respect to x, so we just get e to the x squared times y equals over here, this is just going to be, I'm going to let you do the integration on that, 1/2 e to the x squared plus a constant. So I integrated here and here, and then I'm going to divide through by e to the x squared. So we get 1/2 plus c times e to the negative x squared. So that's dividing both sides. Let's call it c sub 1. Now our initial condition is y of 0 equals 2, so that means we're in this interval, so we can get the c1 from here. So y of 0 equals 2 means that that equation right there becomes 2 equals 1/2 plus, and now when we replace that x with 0, we just get 1 there, so we just get c1, subtract a half on both sides, so we get that c1 equals 3/2. Okay. Okay. Now, going back to where our function was, here's our function right here. So what we know is that y is equal to 1/2 plus 3/2 e to the negative x squared. That's what we got so far. That's only on 0, 1. Now we need to look when x is bigger than or equal to 1. And for that, it's going to, the original differential equation would be y prime plus 2xy, and this time this will be equal to, I believe it was 0. Let's see what this, yeah, piecewise up here it's 0. So 0, we already know the integrating factor is e to the negative x squared. No, hold on. It's e to the x squared, sorry. E to the x squared times y. And we multiply the right side by that also, but that's just 0 still. So this will be nice. This will just be e to the x squared times y when we integrate, and the right side is just some other constant. And so y is equal to c sub 2 times e to the negative x squared, dividing both sides by e to the x squared. So now we know that y will be equal to the first one we got, which was 1/2 plus 3/2 e to the negative x squared, so long as x is between 0 and 1, not including 1. And then if x is bigger than or equal to 1, it should be this c sub 2 e to the negative x squared. So now we want to know what's happening in this transition. We want to make it continuous at 1, so we want the limit as x approaches 1, this time from the left, because we have the equal sign underneath here, so it's defined, the function is defined here at 1, and it's not defined there, so we want to come in from the left side of 1, and that means we want to be plugging into this negative x squared. That must equal the function's value at 1, so the function's value at 1 is going to be c sub 2 e to the negative 1. So that's just going into this one and replacing this x with 1. All right, so let's let x approach 1 on the one on the left. So we get 1/2 plus 3/2 e to the negative 1 must equal c sub 2 times e to the negative 1. We will divide both sides by e to the negative 1, which is the same as multiplying both sides by e. So multiply that by e, multiply that by e, it's gone. And that should be your c sub 2. So if we go in now and we replace this with this, then we will have our function. All right, there's one more. I'm almost there. 58. All right, so we've got 1 plus x squared, y prime, plus 2xy equals some function of x. That function of x is equal to x if x is between 0 and 1, not including 1, and negative x if x is bigger than or equal to 1, and my initial condition is y of 0 equals 0. Alright, so we need to get this in the right form first, so I'm going to divide through by 1 plus x squared. So this function on the right hand side is actually that over 1 plus x squared. That's a little different now, because you got to imagine that this is going to change our function over here. So let's go ahead to get the integrating factor. So e to the integral of 2x over 1 plus x squared dx. I'll let you do that. It's a pretty simple basic u sub. This is e to the natural log of 1 plus x squared. We don't have a domain restriction there because 1 plus x squared is always positive, and that's just 1 plus x squared. Now we multiply both sides by this, and we know that the left side will become that integrating factor times y, and that must equal this side times the integrating factor. Great news. That's just our function of x. So I did this one a little different. Let's look at it on the interval 0, 1. If we do it on 0, 1, not including 1, then this just becomes d dx of 1 plus x squared times y equals x. And now we integrate both sides with respect to x. So we get 1 plus x squared times y equals 1/2 x squared plus some constant. And now I use the fact that at 0, when we plug in 0 for x, we get 0 for y. So I'm just going to do it right now. This left side becomes 0, and the right side becomes c1. So c1 is 0. That's nice. That means, you know, I'm going to kind of go back. Let me go back and solve for y. Okay, so y must be, let's see, x squared over 2 times 1 plus x squared. So I divided this guy right here by 1 plus x squared, and then I'm going to divide c1 by that. Now I'll replace y with 0 and x with 0, and you'll get c1 is 0. Okay, so if you do that, you'll get c1 has to be 0, which means that this could be rewritten y equals x squared over 2 times 1 plus x squared, like that. So that's what y is if we're on this interval 0, 1, including 0. Now let's look at what it would be on x bigger than or equal to 1. So on x bigger than or equal to 1, we get d dx of 1 plus x squared times y must equal negative x, because that's what the piecewise function is over there. And now when we integrate, the only difference we have here is 1 plus x squared times y must equal negative 1/2 x squared plus some constant. And we can divide through again, and we get y equals negative x squared over 2 times 1 plus x squared plus c sub 2 over 1 plus x squared. All right, so far we have this guy and this guy. This is what it is on here, and this is what it is here. But we want them to be continuous, so we need to take the limit, and our discontinuity is at 1, so the limit is as x approaches 1 from the left, because we're not defined at 1 on this one, of this x squared over 2 times 1 plus x squared must equal this guy at 1, evaluated at 1, which would be negative 1 over, let's see, 1, 2 over 4 plus c sub 2 over 2. That's just plugging in 1 for x. Now when we take the limit on the left, we get 1 over 4 must equal negative 1/4 plus c sub 2 over 2. So we get, let's see, add this to this side, so we get 2/4, so that's 1/2. 1/2 equals c sub 2 over 2, multiply both sides by 2, and we get c sub 2 equals 1. So if we just come back up here and replace our c sub 2 here with 1, then this would be the first part of the function, this would be the second one. Let me just double check it here. freehand. What the heck? Yeah, that should work. Okay. So we are done. Thank goodness. All right. Hope this helps.